Hey everyone. So I did not finish this proof. I thought I was gonna be done by now, and I spent hours and hours and hours and basically spent an entire day trying to prove this thing, and got nowhere with it. I did have a few insights as to why I was getting nowhere with it. I was trying to prove an equality between two things. So I was trying to reason basically in not the last video, but the previous video, part I guess 7 of this, and since then I was trying to show an equivalence between the terms before the partition of this data structure and the terms afterwards, and that doesn't make any sense because it's not a one-to-one mapping. It's a partition, right? So you start out with n items on the left, and then before, and then you wind up with n times something else items on the end. So it's not an equivalence, and the everything on one side maps to the other side cleanly, but working in the other direction didn't work right. So actually, that's what I'm going to fix today. I spent so much time like fighting with this in Lean that I finally just got away from the computer and I tried to make some drawings and just write out the proof. I didn't actually upload the one that has all the drawings on it. Maybe I'll do that real quick, and then I don't know if it's worth sharing, but kind of doesn't. Kind of not. Let's see. I'll just do this. Let's hold it up to the camera here. Yeah, so this is backwards now. Yeah, so I mean, like that's the kind of stuff I was doing, just doodling on paper, trying to account for what like not much of a like, kind of not just doodling, trying to figure out exactly what it is this thing does. What it does is the green screen. Magic. So yeah, so this is not. Well, in doing this by hand, like I kind of was performing the sieve by hand, and I realized I came up with a different way of thinking about this algorithm that I think would make it a little more efficient. I think you could, if you have a mutable array, I think you could just generate primes automatically and not have to worry about what am I trying to say? Like not have to worry about. It's not much of a sieve, right? There was a it would just immediately generate them. So I might worry about that later. But like right now, I know this is inefficient. I know that the implementation I have is just ridiculously slow. Not so much that it's slow, but that it just allocates so much memory that it like you can only generate 5 primes from here. But in generating 5 primes, it generates it only shows you 5 primes, but it in doing that, it's generated many primes that it's just not showing you. So that's the idea. that there was a better way to approach that. That you don't have to pay the price until you absolutely need to pay the price and do things a little more lazily, and I think it could work. Plus, I don't know, it's just whatever. But that is a story for another day. So in the meantime, let's work on finding the correct way to get this. Sorry, my little thing is not very organized today. Okay, oops. All right, so this is what I wrote out on paper. This is the proof part of it that I wrote on paper. Obviously, it's on a Kindle. And I saved it to a PDF, and it saved a little background here, so sorry about that. What are we looking at? Isn't there a button that I can use to... so how to show that every term is preserved by a partition. So we have exists n such that our, the rake term n is equal to t. I'm going to rename all these variables. I'm going to go through in a pass and just make sure all my variable names are consistent so that one unified terminology throughout all the functions work. So I'm going to call terms t, I think. N is the input, t is the output. So so if you have a term before the partition, then r prime is after the partition, and then you should still have that. You should still be able to get plug n in and get t out and get the same And the statement doesn't relate these two ends. They're just two different ends, but in fact they are the same number. Yeah. Oh yeah, I didn't even see. I changed the letters even on this page. The fact that the two n are the same and the other arrow was easy to prove, but this is tricky. So it wasn't easy to prove. It was painful to prove, but I did get it proved off camera. Why tricky? And that's because each sequence is chopped up. So it's, again, you're breaking it apart. So I wanted to just like explain to myself by, just on paper why this is the case. And so one argument that you could make is that for all t of the terms of the rake is like a set, right? It's a set of numbers in a sense, and they're generated. It's a thing that generates items from that set. So if I think of a rake as a container, in addition to little pictures I've been drawing about lines on going up and down or whatever, or at a slope. So it has terms and it has constants inside of it. It has sequences inside of it, but it also has the terms of those sequences. So for all the t, for every t in those terms, every t that is a term of the rake, which is not syntax and lean, it's just informal. This is the formula that generates it. There's some constant that is one of the constants tracked by the data structure, and then they all have the same delta term, and then you multiply it by n. So n is the input. So for all of those, that's true. That's just a definition. And then I decided to call the number of constant z, or size, because s is the set of some other set. Actually, I don't think I use set s anymore. I think I have it down to capital R, lowercase r being the whatever. Anyway, so I was using capital K for this last night. I don't know. But then I started saying, well, you're going to use the word K quite a bit, so picking names is hard, especially when you're trying to be concise and whatnot. Anyway, but so K is one of the K's that we have, and it is at the index, here. So the I is actually n mod z, and that determines which sequence of the sequences inside the rake generates the answer, because we rotate through them. That's what that's mod is like a rotate through these things in sequence operator. Because it's the remainder, right? So actually I was doing something with mod right here. You have I20 and you say 3 mod that, well, you're going to get I20 is just the numbers up to 20, and you're going to get a repeating pattern, because that's what it does. So in order to make the choice of which sequence you're picking from rotate, then we use this. So we use a modulo operator. And then in order to pick what number you feed into it, so these numbers, if we wanted to generate this sequence from here, right, you would pick, you would make the sequence, it would be 0. You would take these modulos, right? These modulos. What does that mean? Right. Yes. And then P. I wonder if you can do this. I5. Oh. So P. Rank 1, I5. Yeah. There you go. So so in J, you could have all these sequences running simultaneously, right? I should show that to Daniel, because I think this is probably a simpler way to do what he's doing. So right, and then these would be the sequences 0 plus 1 1. So this is a rake in J. It's this many characters. It's your K's, KS, and then your D, and then they're polynomials at rank 1, meaning that for each one of these, so then you plug in the thing. Oh, right, because I haven't decided what they are. So in this case, D equals would be like 6, and KS would be like 3, 5. There you go, and then those are some terms of a rake. Actually, it wouldn't be that. It'd be 357, wouldn't it? There you go. And then those are all the numbers that that haven't been sieved out yet. Anyway, that's that. And you can see they go in sequence, right? 3, 5, 7, 9, 11, 13. So if you have a rake set up this way, they go in sequence up until you get to this point. It is possible that on the next step, like you wind up going up and then drop back down, and that would happen especially if what should happen with 6 and 7, right? I'm surprised it doesn't. I'm getting off track. It doesn't matter, right? I just want to test this real quick. So you had 5, 7. I don't know how to. Oh, I know how to do that. So you take you take this and you sort it. Oops, that's not sorting. This is sorting. But not. There you go. I know that's hard to read, isn't it? You edit font. So what was I going to say? So you have these things, and I think it goes up to 31. It should be 8 of them. So we say 8. I say we say 10 take of this. And then, yeah, 2 of them wind up being multiples of 5. So we switch those out, which you can do programmatically by saying 5. I'm just showing off now. I don't know why I didn't do this. 5 mod this. And then if we say 0 equals this, and then not, how about not equals this, which would be this, right? Then we take those, right? Yeah, okay, and that should be 8 of them. The length of that is 8, yeah. All right, so then those are the next. That's KS. That's this is what I spent a month on in Lean. Writing it in J is like, oh, to be fair, the implementation in Lean took an afternoon. But anyway, so then D would be 30. So we have D. So we have KS. And then I did like that, and then D equals 30 now. And then we said P at 1, and then I 10, right? And then those are some numbers. That is interesting. What I expected to see was like because this is what I see on the graph, like the numbers wouldn't be in order like this. That would be mad. Right, so the terms of the sequence would be generated like this, and then like this. So we're doing zigzagging up and down the rows, right? So if we view mat this, view mat will draw this matrix and color code the cells. Interesting, and it makes this pattern. So it goes from blue. It gives you a rainbow, a spectrum. Right? This is a spectrum that's being wrapped around like this. That is not what I expected to see. right? So this is a single gradient going through the color wheel all the way from here to here, and I mean like if we I wasn't expecting these to be sorted. I'm surprised that they're sorted. Shape of this. So you do this, yeah, that's it. I'm making a two-dimensional matrix, and we're going to put them all in one line. So if you view mat of this, it shall be one. Oh. All right, because I have to transpose it first. He gave me that. So that's not what I expected to see. So if we transpose it before we flatten it, so this says transpose it, flatten it, and then take the one-dimensional array and make it into a two-dimensional array like that. And then if we view mat this, now we get the clear gradient. So this is the thing that's actually being generated, and they're all in order. If they weren't in order, you would see what I just showed a second ago. You would see some random ordering, or in this case, just transposed. Meaning it was this is the order if you go left to right rather than zigzag on that matrix. Anyway, yeah, so this is a rake in J where you can say how many terms you want. And if you just want one term, then you would get that. And if you took, I guess if you took, there's 8 things. If you took 10 of them, it would give you zeros for the others. Oh no, sorry. Right, because it's doing it for each one. Oh, I see what it is. This is not the same algorithm. This is doing all of them in parallel. So it's passing 1 into each one. And then it's passing 0 into each one, and then 1 into each one. This is making a table, right? So this is the 0th term, the first term, the second term, and so on for each in order. I don't know. I was just expecting to see something different here. I was expecting to see this number be greater than this number. I've got something different here. Because I start with 2, 3. I know I'm completely off track here. This is not important. D equals 6. It doesn't even matter what D is, right? 2, 3, and 6, and then P 1, I 10. Is this right? No. We started with like this, 1. Here they duplicate each other. So it's not quite the same problem, but right, because okay, so the initial idea is that maybe you put 2 here, right? Yeah, you would put 2 here. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's interesting. I was not quite expecting this. I could have sworn that these were you had a situation where they were in order. See, normally you define the evens and odds like this, right? So you have these are the even numbers. They're 0 plus 2n, and then the odd numbers are 1 plus 2n, right? But for some reason, I had it in my head that when you do the very first thing we're gonna do is we're gonna make the ones that are greater than 2. So we have to move these numbers up. So this becomes 2 and 3, right? not greater than 2, greater than 1, greater than or equal to. So to cut these numbers off, we just add 2 to these two numbers, right? And then it shifts over, and now there's no overlap. Huh. Okay, well, so we can do this by hand now. I'll just kind of like summarize what I did on that other page just to get into the mindset of what I did and get better at explaining it myself. All right, let me look at my notes here. So these are, we want to compose these things. So we can think of this as of this p dot as being p is for polynomial. What this is saying is 2, 3, 2, 3 and 3 times y, I guess, the input y. Plus d, which is d times y. Oh, it's actually 2, 3 plus, because these are constant terms, plus d times y, and then for I10, right? That doesn't look the same. We don't know what d is, right? D is 2. That looks the same. Same numbers. So that's what's going on. And now we want to add. So we start, very simply, we start with all of the natural numbers. So I have two kind of like primary rakes, right? So one of them is this. It's called 0. It gives you all zeros. And in fact, any numbers you put in here, it repeats them over and over again. Again, going, so to generate the terms, we would go sideways and then like that. So, and that repeats them over and over again. Because again, it's just picking one at a time, and then adding 0 times the input, right? So that makes it like that. So this is called zir, Z-E-R, zir, or the zero rake. And then we have the next one is called nat, which is 0 plus 1 times y, right? And that gives you the natural numbers. If you want pos, that would be the positive numbers. And if you want the evens, or the evens and odds, right? So we start with this, these, and then we say, okay, but I want to exclude 0 and 1 because they can never be prime. So we start with that. So that one is called 2GE, 2 greater than or equal to. And those are the three things that I predefined: 0, nat, and 2GE. I had previously had a greater than or equal to operation, and I just I removed that. Oh, this is a mathematician's apology. Not important. Just Googling that. Okay, so anyway, now I want to take this and I want to extend it. So I want to compose this with another function. This would make a good demo, right? 0, 1 plus 2n, right? So let's start with 2. All right, so 2 plus 1y, right? Whoops. I10, right? These are my inputs. And we're going to compose that with this. So we're going to put these two together. These are the evens and odds, right? What happened here? Right, because this says y, and I didn't actually write it. I copied my notation and I didn't translate it to J. right? So you compose them, and what did this give us? Well, it gave us the evens and odds together, right? So, so it looked exactly the same, right? I mean, there's more of them, but that's it, right? So that's what's on the right hand side, and then we compose these two functions, and they come together. So what we're doing when we do this is we're basically, we're taking this input, right? So it's as if they are the y is being replaced by that. So to do the composition, we do this. We just remove this. Right? I like that. I like this proof. And then because I'm one of the things that got me into theorem proving and Lean in particular is you can overwrite the syntax. I really want to make a system where you can do like calculational proofs in J, but then back it up with, I mean, you can, like, that's one of the ideas of a APL J-like languages. Iverson was, in his Turing paper, one of his criteria for a good notation is that it should be amenable to formal proof. And I think this is a good demonstration of that. So here I'm combining these two things, and what this is this is what a composition of two rakes is. Rakes looks like, and so then what we're going to do is we take these two numbers, and we'll move them over, and we have to run them through this formula, right? So 1 times these two numbers plus 2 would be 2 and 3, right? Right, and that gives us the next numbers. And then what we do on the right hand side is we're gonna partition, and partitioning is the following, right? So we've so back up a second. Okay. So basically, this is our sieve. We've identified the very first number in the sieve is 2. In the rake is 2. That is our prime number that we're going to now cross out. So how do we cross it out? Well, we multiply, we move these over. Wait, am I doing it right? Yes, we move these over. So we multiply them by 1, 0 and 1 times 1. And that gives us 0 and 1. And then we add 2 to them, so we get 2 and 3. And then we have to partition these. We have to partition these so that we can isolate the, let me know. So that gives us too much stuff. Can we do it like that? Yes, but we don't want that like that anymore. Okay, so this is how we'll view it. So we do it like this. So let me put it back how it was. 0 plus 1 times this should give us the odds and sorry, it was. This is the nats composed with the nats, so it gives us nothing. This is an identity operation, right? I10 is this, and so this whole thing is an identity operation. We're composing the identity with the identity. And then we say, okay, well, I want 2 or more, so I have to add 2 to this, so we just add 2. There we go. Now we start with 2, okay? And we said these two numbers cannot be prime. 2 is the first prime. Okay, we have 2. I want to scratch off all the numbers that are multiples of 2. And so we say, well, we add this number over here. So we add 0 to this and get 2 again. And then we take this number, we take this line, and we're going to partition it into 2 steps by composing it, just as we're composing now, with the following. We're going to compose 0, 1 times 2. Right? But let's not make that. Well, that'll work, but I'm not sure how to show the next step. Okay, so then, okay, now we say, well, okay, that's great. So we're going to get rid of the 2 line. So that was this one. So this constant goes away. And we're stuck with 3. And so, I'm sorry, actually what we do is we say 2, 3 over here, and then we set this back to Yeah. All right. So this is an identity, and that cancels it out. Now we have these two. We're going to get rid of that. Say, okay, well, 2 is a prime number. I'm going to get rid of that. Boom. We have 3, and then we're going to I got it now. We got 1. We're going to do it like this: 1, 2, 3, with the number 3. Right. And then we have these things. Right. Nope. I didn't update that number. Yeah. So you put the 2 here. You don't just get rid of it. You add it to the accumulator, or you multiply the accumulator here. All right. So there you go. And now we have these, and then we say, okay, well, 3 is gone, and we're going to keep 5 and 7. So we have 5 and 7. Those are our new sequences. We're going to move the 3 over here to make it 6. And then because we took the 5 out, we're going to go all the way up to I5. Okay. And that's the next round. And that's where we were just a minute ago. I need to work on this a little bit. I definitely need to work on the presentation. So we can move this to a single number. So this will be, we're going to count up to that number. And here we have a nice little fork. Oh, how do we do it? We say we put the 5 over here, right? And then so we want that. I think you can say, I think if you do it like this, 5. I'm trying to see how to make it a dyadic hook. I'm not sure this works the way I think it does. I don't normally do it this way. It's completely off topic, right? So this is, because you have to say y in here. And then we're going to say I. No. This? No. It's a dyadic hook, right? That's almost. Yeah, that's it. Is that it? I think that's it. Putting this back to where it was before, that would have been 3 times 3 and 2 and 3. No. No. No, I screwed something up. All right, it doesn't matter. I'm completely off track here. Anyway, the point is that you know, as you plug these numbers in, what winds up happening is that you accumulate them over here on the left-hand side. So this kind of like stays the same. Let's just call this x, right? Y. And we'll compose it with this number 5. So I ix plus x times y. Okay. Not quite right. There we go. That's still not quite right. Because this should start out with 2, 2, 3. What am I doing? Ah! Wow. This is why you plan. This should be the identity. Yes. Okay, we got the identity, right? And then we map that in there. Okay, and these are all the numbers. And then we've now well, if we just wanted to talk about sequences, we could just talk about y, right? So we could say iy times y. Okay, right. Which in this case now is just it's this, right? The whole thing is just this. This should be the identity sequence. And this gives us 4 and 5. That's not quite right. 0 and 1 gives us 2 and 3. We add 2. Oh, right, because it should be 1 plus 2. This is, no? It should give us 2 and 3, right? What is this giving us? Ah! Is this? This times is what I want. That's why. Right, okay, there we go. There we go. But no, that's not right either. You don't just add the multiples. You take this. Sorry, I'm just being really dumb here. The identity function would be for a number y. You want to take that. So this. P y, right? is this. Sorry, I'm just wasting time here. I want to generate the wow. I want this. Right? Those sequences as polynomials. Like that, right? Yeah, those polynomials. Except not this. 0 plus should be that way, right? No, that's not it either. There we go. All right, so now, yeah, okay. So this is, no, but we don't want that. We don't want that, we want this. 0 plus 5i, these are the polynomials. These are the k and the d. 0 plus 5i of arithmetic sequences. 0 plus 5i, or n, 1 plus 5n, 2 plus 5n, 3 plus 5n, 4 plus 5n. So that is, this is a rake in J basically, because they all have the same delta term 5, and then they all have you're counting up to them. I don't actually have a thing to generate this number or to generate this structure, but it would just be, it would just be the number where the delta is whatever number you're feeding in, and then the k's are everything up to it. I do that implicitly. Okay, so this is the partition step. So when you plug in partition 3, what it's doing is it's composing whatever rake you have with this rake, with this structure. All right, so this is the partition. I should write this down somewhere. I should record it in a video so that I'll never look at it again. Where's my little notebook? Hang on a second. I'm going to call this J realz. This is, what would you call that? That is gives you the arithmetic sequence that we compose in partition. Okay, so again, I said you could do this by hand though, so it's, I should just go back to doing that. So we said we have, look at I just copy what I did on paper and I don't have to like, right? So we have 2 plus 1 times y. I10. I10. And we're composing that with 0, 1 plus 2 times y. I10, right? How do we say each? What? I'm just being stupid now. I don't even know why I'm doing this. Why I'm recording any of this. Cut all this stuff out. Oh, maybe that's. Okay, so this is the identity. 4, 5. This is the identity. There we go. And maybe we actually did want each. I even put in 0? Term 0 of each one of these? Because term 0 is a constant term. Okay. So then let me say, okay, I want 2 or more. Yes, there we go. And we say I want, okay, so I'm going to partition this now. I'm going to partition it on the number 2. I'm going to move 2 over here. And then I'm going to multiply. No, I'm going to do this, right? Let's say 2 times 0, 1 over here. And then leave the 2 in. Nope. I had this before. That's it, right? So okay, so that was the step. This is what I had before. 0 plus 1y, 0 plus 1y, and then I say, okay, well, I want to increment that by 2. So I do this. Nope. We start with 0, right? That's step 1. Let me paste this. Right? And then I add 2. Boom. Okay, that's the next step. And then we partition. So we say 0, 1 plus 2. Right? And we get those. Okay, so now we're gonna plug those numbers in, and we're just gonna put this back to the identity basically. This is telling me what the partition does, right? So we'll say 2 and 3 plus 1. And then we move the 2 over here, and we set this back to 1. Right? Okay. And then I kind of like that the box is gone. That seems right to me. And then we say, I feel like we should have gotten here on the last step, but I'm just going to go with it. This does look right. And then the next step is that we take, okay, did I have to do it over here? And we wind up with 3 and 5. And then the next step, we partition this, right? 3 plus 2y, that's what I have. Then we put 3 over here. 0, 1, 2, 3. We have this, right? We get 3, 5, 7. Yeah, so we scratch off the 3. Put 3, 5, 7. We scratch out the 3. We put the 3 here, said. and we do this. And then we say, okay, or we don't do this step. This is not an important step. Then what we do is say, okay, we know 5 is going to be the next one. So we partition by 5, 4, 5. Let's say I5 times 5 times y, which is 0. So we just say times plus 5, right? So this is the transformation I want. Yeah. Okay, so we do that. This is also the partitioning step. Well, it's not. These are the coefficients. I see. This is a function, right? So it's not really y. Y could be anything, but we're only looking at the first term, 0. Okay, so that's what's confusing. Yeah. I wanted to talk about this just from. Let me stop this. I mean, I do want to. You keep doing this, right? And then you keep doing this step. So we're going to multiply this, and we get 30. And we're going to put these numbers in. There should have been more. Is it because they're 3, 5, and 7? No. No. They're not. There shouldn't have been more. This is right. And we haven't done this step yet, so we only have 1 and 2. Right? Go from here. Man, what is this? 3, 5. That's the next step. I don't know if this is making any sense. Is that what I wrote down? 2, 3 plus 2y, yes. No, I wrote it down differently. I'm just going to do what I said, not necessarily. I wrote 2 plus 1 times y. And then what I wrote down was 0, 1 plus 2 times n, like so some number n, right? Let's say n equals 0 for now. We get 2, 3. And then I say, okay, I'm gonna put 2, 3 over here. No, how do we do that? What we take is these numbers, right? And we put them in here. So we say 0 times 0. Right, so I did this in my head, and I got these two numbers. This is the worst video I've ever made, and that says a lot. We put this in here, and we put the 2 here, right? 2, 3 plus 2y, and then, right, and then we get this stuff, but we have to extend this out here. We put another number here, we add this here. We move it up to 3, yes, okay. Two, 3, 4, 5, 6, 7. That doesn't look right. Because again, this does have to be a function, right? And we have to compose these functions. I'm just being stupid. I'm not going to evaluate anything, right? I'm just going to write what I wrote, okay? So that would make more sense to me, right? All right, so what I said was 2 plus 1y, and then, I guess, write it in J notation. 1 times y, and I wrote, I guess this is informal notation over here, 1 plus 2 times n, right? Whatever n is. N is the input to the function. So, goddamn. That's ridiculous. How do you scroll in this thing? Yeah. Okay. And then I said, you're going to apply these numbers. So 0 plus 2n added to this. I guess I did this in my head. Like, what did I do? You know, when you compose these two things, you have k plus d times n, right? And then you're replacing that with, k prime plus d prime times n. That's how you compose them. And so you wind up with k plus dk plus dd times n, right? dd prime times n. So the way this works is you take the number you currently have, the current multiplier, which is 1 here. I should have written this too. All right, so you say 2 plus, you take these two numbers, you move them over. 2, 3 plus 2 times y. And that comes from multiplying this 2 times this 1. This 2 times these two numbers, 0 and 2. You multiply this number times, yeah, right. K, so you take the old d, this is d, multiply by these two numbers, you add it here, and then you multiply this number by the new number. Okay, got it. But yeah, this deep. I'm embarrassed to make this video. Okay, but it's cool. This is gonna be cool if I this needs to be. All right, so now we're gonna do the same thing, but we're gonna compose it with 0, 1, 2 plus 3 times n. Why 3? Because we're going to remove this 2. That was the 2 that we had before. Or no, this is what we have, right? It goes in a zigzag pattern. You start with this, you partition it on this, you get this, you partition it on this, you get the following. So we're going to plug these two numbers in. So we're going to take k plus 2 times these numbers. So we're going to say each of these numbers. So we're going to say 2 plus 2 times. So these numbers are multiplied by 2 leads to 2 times these numbers leads to 0, 2, 4. So we're going to add 2 plus those numbers. We get 2, 4, 6. That cannot possibly be right. Oh, but we're going to scratch out the 2. All right, so we drop these, and then we get 3. I don't know how to scratch something. How would I scratch it out? Like mark it in like a different color or something. Red. We say 3 times those numbers. So 3, we actually 3. So it would be 0, 3, 6. Let me say 3 times that. No, but it's no. was 2. I'm feeling so stupid right now. I'm on camera. We scratch out the 2, and then we multiply 2 times these numbers because we're using this formula right here. Okay? So to compose these, we multiply 2 times those numbers, right? And then we add the original number. So 3 plus 2 times these. So 3 plus 2 times 0 is 3. 3 plus 2 times 1. 2 times 1 is 2, so we get 5. And then we add 2, and we get 7. And then we say, okay, I'm going to move the 3. I'm going to cross this 3 out. That's my next prime. And then, so when I cross it out, I put the 3 here. We don't even need the y, right? We just need 2 times. Maybe it would make sense better in the diagram if I marked it off here, right? And then I do this, right? Okay, so I don't know. Let's go back to the way I was doing it. All right, so we have 3, 5, and 7 times 6, and then we're going to multiply it by 0, 1, 2, 3, 4, 5. No. Yeah, because you gotta cross it off here, right? And then you say, okay, I'm crossing it off here, and then you say, okay, I'm crossing off 5. Boom, and then you say, okay, 5, 7 plus these. So you move the 3 over here to the 6. You make that, something new. And you say 0, 2, 3, 3, 4, and then plus 5 times n. Okay. So we do that, and we ignore this 5, and we get no, I've done something wrong. We should have had 5 here, right? And then when we plug these things in, we only do the 5, and then we get 5 plus 2 times these numbers. So 5 plus that would give us 5, 7, but we want color 5, 7. I'm so stupid. I don't even know what I'm doing. Like I did this and it was like so easy on paper. I'm just confusing myself, right? This is wasting everyone's time. Say 0 plus 1 times whatever. We don't partition that, so we say 2 plus 1 times whatever. That's the greater than equal to step, and b greater than equal step. Now we're going to partition this 2 times 1, and we partition on 2. Now partition on 2. All right, so we do that, and we get 2 we get 2 and 3. Right? That 2 and 3 are preserved. Okay. So we haven't marked these off yet. We haven't. This stays normal. Mark the 3 off now. This stays the same. I'm sorry for wasting everyone's time with this. Now we mark the 3. Okay, now we identify. So here's where we identify 2 as a prime, right? Here we say 2 is a prime. Oh, a nice bright color. Here we say 3 is a prime. And that's why we multiply by 3. Right? And then we say 2, or, like we're ignoring this one, but we say 3. And we count by 2 is 3, plus 2 is 5, plus 2 is 7. All right. We strike the 3 off. And then we multiply the 2 that we have down there by 3, so we get 6. We identify 5 as the next prime. And then we do I5 over here. Okay. Next step. We scratch off the 5. We keep the 7. We scratch off the 5. No, we have, okay, next step is to apply these numbers. So we start with 5. We say 5 plus, we count by 6s. 5. Right, because now if we count by 6s. We say 5 plus 6 is 11. 5 plus, then we get 17, plus 6 is 23, plus 6 is 29, plus 6 would be 35, but we don't count that high. We do 4, we do 5 of them. 0, 1, 2, 3. 0, 1, 2, 2, 3, 4. That's 5 of them. And then we do the same thing for 7. 7 plus 0 is 7. 7 plus 6 is 13. 13 plus 6 is 19. Plus 6 is 25, which is our multiple of 5. And then we add another 6, would be 31, and that's it, as high as we go. And then so we say, okay, 5 is this, and then 25 is bad. Okay, and then we say all these should be in different colors too, right? Like this should be like a separate step that gets added, right? This should be part of the equation. Please feel free to skip ahead in this video. If you're not, no one's watching it live, I guess. Plus, and now we're going to take the 5 and go 30. Times, okay, and this is the new rake, right? 30 times. This is the new rake in J. Oh, and this is why this is why it was coming up like that, because now I do a sorting step. Why am I out of frame? Okay. So this is what was causing it to do that. But what I did instead, right? Because I didn't like that. This is what caused it to go out of to get a kind of a zigzag, or kind of a sawtooth pattern. And what I did is at each each partition, I sort these numbers. And so I generate them in a different order. So rather than doing this, I don't do it in this order. I invert the for loops. So I do 5 plus 0, 7 plus 0, 5 plus 6, 7 plus 6, and then I keep adding 6 to those pairs. So 17, 19, 23, 25, and then I would immediately cross this off. This one I will cross off as well. This is like bad way. Bad order. Inverted for. All right, 25, and then so I need to add. So let me put commas in them, right? So here we have 1 comma, and here we have a bunch of commas because we're 5 commas probably. All right. So then 6 plus 23 is 29, 25 plus 6 is 31, and that's it. 30 times. Okay, and then we identify a 7. So we put this over here. Point is, you can do this by hand. It takes a little more practice, but you can. And then I say we scratch that set. So we say 7 is the next one. 7 is going to be our next prime. How many colors, variations of red do I have? 7. They're all 5. Right? This should be 3. All right, so 7. Okay, so then we're gonna do this with we're gonna multiply 30 times 7, and we're gonna whatever. Okay, but for each one of these now, except for 5 and 25, we're gonna multiply it by this. We're gonna do the same thing. 5. So we're gonna copy these numbers. This was the key idea, right? That you copy the numbers so they stay in place. You're building. You know, if you're generating your list of primes, you can just generate it in place, and that's why I think you only need like 1 array to do this. How long did it take me? It took me 1 hour and 13 minutes to get to this point. I know I didn't only talk about these things, and we got to get rid of the commas because we don't know. Okay. Plus 210 times, and then now we plug in these, and we gotta go up to 7, right? 4, 5, 6, and go by 7 times n. Oh no, we have right. So it's going to be a bunch of numbers now. So that was just the first set of numbers, and then we have to add 37, 41, 30 plus 13 is 40. What? 30. 43. Is that right? 47, 49, which is the multiple of 7. Right? I'll do that in a minute. I'm just going through and adding these numbers. 17, 19, 23 is 23 plus 30 would be 53. 59, 61, 67, 71, 70. Where did I stop? 67 is not on the list. Stop here. No, you don't. You don't stop. Keep going, but that's the end of the first group. But you keep doing this. You keep doing this, and every number you're generating here is a prime, except so 49 was a prime, or was a composite. All right, and then we're going to do in that group we got to do 7 more of them. So we start at right after that we do 30 plus 37 is going to be. Right, see, I don't even have to worry about these numbers anymore, right? You just keep adding 6 to the number that you're looking at here. So if you have a cursor going across here, you generate this stuff, and you're generating primes as you go along. So all you have to do as you go along is you check that the number that you just generated that they're about to generate is it a multiple of this number? If it is, right, you do 1 division at every step to check. And in fact, you know that for every, so there's 8 numbers here. For every 8 numbers, only one of them is going to be divisible by 7. Oh, sorry, you're partitioning on 7. So of the 7 that you're generating, exactly one of them will be divisible by 7. And really, you could look at this first number and you could say, well, okay, 7 is divisible by 7. Therefore, the first thing that we're going to get rid of is step 0 here. Okay, then on 11, what is 11 mod 7? Well, we get 7 mod 11 is 4. So the 0, 1, 2, 3, 4. So if you count that way, mod 4 is the one that's right. So basically, you could look at these terms and then just immediately add that's clunky though, isn't it? It's very hard to do it this way because but if you do it in this order, it's very easy. Right? Like this is a coincidence, isn't it? This is not right. This is not what I was did I do it the wrong way? 11 mod 7. Right? That should be mod 11. What about 7 mod 30? Sorry, 11 mod 30. 8, that's not right. What am I looking for? What am I looking for? I'm looking for, I'm going to take this number, and of that, I'm going to generate 7 numbers from this 11. Oh, I see. This number did not come from that 11. That was a pure coincidence. Maybe it's not a coincidence. Let's see if the pattern holds, but man, it's not even a pattern yet. But like 7 mod 7 is 0. 11 mod 7, or 7 mod 11 is 4, and then that came out in slot 4, and that's not what I was expecting. I mean, you can certainly look at these numbers and figure out of the ones you generate in this order. Which one you're going to skip. And then you're basically, if you switch the for loops, you basically transpose that matrix. So I actually think, yes, that is to be expected, that on this one, whatever 13, 7 mod 13 is, should be 6. So the sixth term here, the next to last term, should be the one that, no, the last term, right? Because right, we're doing 0, like, so it would be, so what's 13 plus I7 is these numbers. Am I doing that right? No. 13 plus 30 times these numbers. 13 plus 30 times I7. And then for each one of these, we say 7 mod. And I'm just going to stop. Sorry. I7. Makes that fancy pattern. So all the blue ones are the zeros. 0, 1, 2, 3, 4. We're generating them in the other order, right? This order. Which is the same picture, but just transposed. Kind of hard to tell, right? It's not. Yeah, see, yeah, okay, so we got the red one up down here, and then the green one over there. I don't know. I'm wasting time. I do want to talk about this in my video, so it is good to talk it out. I just don't necessarily need to be talking it out on camera over here. The point is, I'm not going to continue this. The point is that you can generate these numbers sequentially like this just by doing a nested for loop, and you know which one you're going to scratch off immediately, and so you can treat them as like you're not really, like, you are implicitly scratching things off in the sense that you're eliminating items from a set. But if you treat these as the coefficients of arithmetic sequences, so you have so this is the rake, right, with all these things in it, and you compose these two rakes, then like what you wind up doing is a nested for loop where you do one division on each thing and you generate a bunch of primes. And you only do one division per, you do less than one division per number. Per prime. You do less than one division per prime if you do it this way. And it's not even a division, it's a modulo, right? You take the remainder. So like I think you won't actually know what these patterns are, but you only have to look at the first ones that you haven't seen so far. The point is that you see what it's doing. Like if you kept these in memory, you could just say, well, my array is now pointing here. And you know, if you're using a language like C where you can move the pointer for the array, you could just keep sliding it along, and then now you start your array at the next slot. And then you just do, you know, you generate the, I bet there's a way you could figure out how to generate these in the right order. Like even if you just like kept a scratch buffer that says what the numbers are, I don't know, like you could figure it out. I mean, I'm already doing it. I'm already like my algorithm in Lean is already generating these in the right order. So you would do so basically you could generate this by hand if you practiced enough, and you can do it on a computer with a mutable array. It doesn't even have to be mutable. It could be an immutable as long as you can keep growing it, right? And so you could do this in, you could generate, you know, if the primes are actually out there in you know, distributed the way that Euler and Riemann and all them say they are, which I mean we expect them to be 1 over logarithm of n, right? I don't know if I can do anything with that fact. I don't know what I can get with, but basically here's an algorithm that generates them in a very short amount of time. That's all I'm getting at. But what's interesting is it was hiding behind an algorithm that when you first look at it looks like it's extremely memory intensive, right? Because to fully flesh this out, the way that we've stated the algorithm, or you know, or that Daniel presented it to me and that I've been presenting it, is that you generate these sequences and at step 1 your array grows by 3, and at step 2 your array grows by a factor, not by 3, by a factor of 3, a factor of 5, a factor of 7, a factor of 11. And so to report the 7th number or the 5th number, you have to have generated 2, 3, so 1, 2, 3, 4. You know, we basically generated 210. No, not, it'll be some number less than 210, but something on the order of 210 entries to report 4 numbers. And then the next one we report will be 11, and then we will have, you know, 7 times this, right? I calculated what these numbers are, right? The way that this thing grows is, is I10, right? So the first 10 primes are these, and then we're going to take the running sum of them, right? So you have like a million. This is 500,000. This is 10 million, 9 million, right? Is it? Yeah, 9 million. There's a comma there, and 9, right? So you have 9 million numbers to generate the number, the first, right? But if you do these 2 optimizations, so 1 is to write it in place, 2 is to, you know, generate them lazily, and I guess 3 would be to skip the one that you know is going to be multiple. Well, you've it's not quite this number. Not quite this number because you have to subtract something at every step. But it's on the order of this number. like I think you wind up subtracting. Well, I think the number that you wind up subtracting is one. You know, if the prime is minus this, and then the running sum of these. This doesn't have a name, but you would subtract this. So if we call this B, so let's make this like 20 of them, and we call this A. Okay, load plot A, comma B. Okay. Well, it's kind of hard to see, but that's that line right there is the smaller number. That's the ones we're subtracting, and these are the ones we're adding. If I did that right. Let's just do. Wait a minute. Hang on. I didn't do it fair. Okay, but yeah, there were zeros in there, but that's the right number. Let's do that again with 20. It padded one of them to 0. This is the actual graph, but it's not much better, right? So this is how it grows. This is a factorial curve, so it looks like it's completely flat because at any step, any magnification that you look at it, it's going to look like this. And you can see these are just astronomical numbers, and these are small. But every number that you generate is prime, so you're not. It's not just that they're likely to be prime. If you generate them and sieve them at the same time, then even though it's growing like this, you're generating these in linear time, and then sublinear time. Well, linear in the number of primes, and which is 1 over log of something, which I think that you can make a good argument. The computational complexity of that. I don't know how that compares. That seems pretty good to me. I don't know if you can do better than that. Actually, I'm somewhere I have a tab open that has like exactly this kind of argument about other things. I was just looking at this earlier. But I don't know. LeanSieve complexity, algorithm complexity. It doesn't matter. I'm not going to look for this now. But the point is, like this is pretty decent. Classic sieve of Eratosthenes takes n log n time, n log n. I don't know. But I'm thinking this is a pretty darn good algorithm here. Except it's just, as I said, it's hidden behind this idea that you have to have this explosion, which you don't, because you can generate it lazily, and if you do, then it's gonna. You can do it on paper, and you're gonna generate the prime numbers at every step. Every number that you generate, if you sieve it immediately, like this, is going to be prime. And if you don't care about the order, you could do it in this order, right? If you don't care that they're ascending, you could do it in that order. I just think that's interesting that at first glance, like we were talking about this, as if it were the most inefficient algorithm you could imagine, in terms of speed, right? In terms of how much memory it takes up. But now I'm thinking this is like, I don't know how you could do better than this. Like you're generating every prime in order in like 1 step per prime, right? Like even less than 1 step per prime, 1 step per number of primes. It's like incredibly fast. It doesn't work if you don't do it lazily. It does not work, right? Is that true? I'm not sure. I don't know. I'll have to think about that. Okay, I'm completely off track. This is not what I set out to do. Okay, and that brings me to the other thing I was thinking of, and I just wanted to talk about this a little bit for just I'm going to go back and watch these. So this is kind of talking to myself, but the idea is that's been on my mind is how easy it is to get caught up. Yeah, I have this general idea about user interfaces, right? And they have to do with the idea that as a human being, you only have so much working memory in your head, and some of us don't have very much at all, right? So it's very easy for us to get distracted. I think that's a little bit of what ADHD is all about, and it's easy to lose context, to lose the context of what you're looking at. And so when you have a screen in front of you, what that does is it augments your working memory. So the working memory in your head is augmented by what's on the screen. And so if something is in plain sight, you want to remember to take take something to work in, anybody who still goes to work as a commute, you put it by the door, you put it somewhere where you're going to see it, and that will remind you to do it, right? So you're using your visual field as a way to augment your working memory. And what tends to happen is if you have something that uses a lot of like computational resources, then that will max out the registers in your brain, right? The amount of RAM that you're using that is available to you for like tasks, right? And so if you're doing something that requires a lot of work and you don't have a good, like everybody has a limit, right? There's a famous paper called The Magical Number 7 plus or minus 2 that talks about like how many just like discrete chunks of information a person can hold in their head. And if you don't do chunking, if you don't organize your thoughts into chunks, it turns out that most people can without training can memorize. They can store a 10-digit number in their head, basically, plus or minus. That's why phone numbers are about that length. And okay, that might not be the right number, but there is a limit, right? And it's a small limit. Like you only have so much working memory, and the more you have in your head, the easier it is to forget one of those things, to drop one of the balls that you're mentally juggling or whatever. So a good user interface gives you some kind of cognitive support. And Lean, the theorem prover and the user interface that we have in Visual Studio Code, gives you a kind of goal-directed thing. So it's always showing you what your next immediate goal is. And it's always showing you, so bring it up, right? What am I doing? Wrong one. So where's Lean? Lean? So over here, you've all got, okay, so like immediately I clicked on what was in my visual field. Like I clicked on this. This has nothing to do with anything. Like I just responded to that. I know that's like Git source code control. Like this is the things that I haven't checked in. Like I immediately looked at that and said over here because like I'm on autopilot because I'm talking and it's like computationally intensive for me. I'm not good at talking. But like just glancing over this, I don't know what this means right now, but I see this. This is where my eye lands, and I see, okay, this is the thing I need to work on. Of all this file, there's one line that's yellow, and that's what I need to work on. And that's the thing that this video is meant to be about. And then if I click on any line over here, it tells me what my goal is, which is to prove this line from these facts, okay? And what can very easily happen, I've noticed, is that if I type the wrong thing here or I see something plausible, my brain short circuits and I chase this goal, even if this is not the goal I should be chasing. And especially as I jump around, it's like, well, I know that in general I want the proof flows from top to bottom, and things that you don't need to be down here, right? You need to be at the top one. If there's multiple lines that are broken, you need to be at the top one, working your way down. If it's yellow, it doesn't matter, right? Yellow means that you're using a proof by sorry, right? So you've temporarily said, okay, I believe this to be true. I'm gonna keep it as true, and so the things underneath it can be marked as you can treat them as they're depending on a rock solid fact here, but you still had better be able to go back and verify it. And what I've noticed is that it's very easy to get caught up looking at something. I mean, for me, I get very distracted easily. But to chase the wrong thing down the rabbit hole because I didn't stop to think whether this is the thing I actually want to be proving or not. And I think that's a really big danger because, as you may have seen from the length of these videos, like this one in particular, I'm just rambling, I'm just talking. But most of the other videos, I've been working the whole time, and it's 4 hours, 5 hours, and I prove like 2 or 3 statements. I think last one was a 2-hour video. I proved 1 statement, and I'm sure I made some tangents and I started rambling because I get caught up in my own. Whatever I say, I go up. I go. There's a reason I call it tangent stream and tangent storm, right? And I guess what I'm getting at is that it's just very easy. Like, on the one hand, it's this user interface is very engaging. Everybody says that a theorem prover feels like a video game, and I would have to second that. Like, it feels like you're maybe not a video game, but you're solving a puzzle. Like you're solving a puzzle, and the visual aspect of it, the user interface, just this little stuff over here, the thing that is always showing you a goal, and sometimes they're easy and sometimes they're hard, and when they're hard, you can break it down into something that's easy. Like, that is very enticing, and you like this has been extremely difficult mentally for me to do this whole time, but it doesn't feel hard at each step, except when I'm doing division, right? When I'm doing something with natural numbers where the theorems just aren't there. What it feels like is I'm in a search. I'm looking for something that I know should be there and it's not there. Because this is not again, I knew this would work before I wrote it. It was obvious to me that it would work, and I just wanted to prove what was in my head, right? Not all of it was obvious to me, like the fact, what I was just talking about it being very efficient was not in my head until until I started drawing it on my Kindle yesterday in order to get away from the computer and get away from this user interface. Because every time I sat down to draw this, or to prove this statement right here, this particular statement, I would get lost. In fact, when I wrote this down, I wrote this statement the opposite way. I wrote down what I thought I had proved over here, which was the opposite way, right? Because I'm not, I know what I set out to prove and I have some awareness of what I'm doing, but this statement says that for every new, after we do the partition, if there is a new one, if there is a term in the new rake, there was a term in the old rake that corresponds exactly to it, right? So the set was preserved, or rather, nothing new was added, right? Nothing new was added, nothing was taken away. They're the same. Is that right? Is that what it's saying? Even now, it's not clear in my head. I know this statement is true. I don't know exactly which one it means. Right? It's same. So it says, if there is a new one, if there is a t prime, this should be called t prime now, then so what this should now say is it exists n prime such that r term n prime, r prime term n prime is equal to t prime, is equal to t, because t stays the same, then there was also one before the partition, right? So we didn't add anything. That's all it's saying, is that we did not add anything. And then this one is the one that says if there was a partition, we didn't drop anything, right? And this is the one that the idea that we didn't drop anything is hard to prove. This one is easy to prove, right? So, but I got them mixed up, right? And because I like you would think you'd have to know like precisely what a statement says in order to prove it, and in a way that's true. But I was working on the double arrow, and so it wasn't clear in my head which one I was proving at any given time, because in my head I thought they were equivalent. They're not, right? Because again, this is a I think they call it a so this is, so we're going, this is a, would be a well, this is the inverse, right? So it's called an anamorphism, which is just a fancy way of saying you start with a small list, you get a big list out. You put a small, you start with a small thing, you get a big thing out. So it's like anabolic steroids is how I remember. Like you know, causes you to grow. And an anamorphism makes the shape bigger, basically. And that's not that I know anything about category theory, but that's a word I picked up from reading Haskell. Like this kind of mapping on a list. If your list grows, that's called an anamorphism. So what? The point is that it's easy to take the big one and say, well, everything that was in the big one came from the small one because I have a formula that says, well, this is how it maps, right? This is exactly where it came from. The formula being this, right? The term simp, right? That or even just the definition, right? I guess we do partition. Sorry. Again, I just looked at something on the screen, and I said, oh, I started talking about that rather than actually thinking through and saying that, right? And like that's just something that's hard for me to deal with. That's a mental thing in my head, but I think everyone has this. People talk about like mindfulness training or the difficulty of like learning to lucid dream. If you want, lucid dreaming is when you're asleep and you are dreaming and you're aware that you're dreaming. And one of the ways you can train for that is to try and constantly ask yourself, "Am I dreaming?" Right, and just like periodically. And maybe even again use something in your visual field. Every time you see your hands, try to remember to ask yourself, am I dreaming? And then usually the answer is no, even when you're dreaming, because everything around you looks like it's normal. But so the test is to like try and read some text or something. And usually in a dream, if you try and read text, for whatever reason doesn't often work out for a lot of people. I once was in a dream. I looked up and there was a couch flying overhead. I don't know if I was in the couch or whatever, but there was a couch, somehow involved a couch that was flying. And I said, oh, am I dreaming? No, this is fine. Right? Because my brain just, you accept the dream world. Anyway, the point is that it's easy to forget to be aware of something. And so if you have a user interface that's going to suck you in the way a video game sucks you in that sense, I do believe this is like a video game. Because a video game is also that same kind of thing. A video game controls the screen, and the screen controls your brain. And so you're constantly responding to stimuli in your visual field that keep you engaged with a video game for hours. And you can, people who have ADHD like me have no problem focusing on an engaging video game for hours and hours and hours. And if work could be like that, then we'd be phenomenally productive and effective. And I see the user interface here as something along those lines. But I have now learned that there is a danger to that. And to be fair, with Lean, the danger is partially that partially that the thing that I'm doing, proving, is something that's very hard for me. Like I'm not I don't have a lot of experience making proofs, so I'm spending a lot of cycles, mental power, working on just deciding what the next argument should be, and I'm not spending a lot of time on meta-analysis. Like, really, should I really be trying to prove this statement? Is this statement true? Do I believe this statement is true, and therefore I should try to prove it? Right. So it's very easy to get sucked up into that cycle and continue working on a puzzle. The puzzle being trying to solve something that is not true, and you would know it was not true if you just stopped and thought about it. Right. It's one thing, like, this guy Hardy. I was reading this book about him, and it's called The Mathematician's Apology. Well, he and Littlewood, Hardy and Littlewood were like the preeminent mathematicians of their day in England, right? So for England, they were the guys. Littlewood and Hardy and Littlewood. Right? Somebody said that at least in English mathematics at the time, the greatest mathematicians were Hardy, Littlewood, and Hardy and Littlewood. Right? So those are the right? They had a thing going on where they would collaborate on papers, and they would always joint publish stuff that they had even the slightest they said one word to each other, they would always publish it together under the same name, whether the other one was involved or not, and everyone knew that. And that gave them a lot of freedom to like bounce ideas off each other, which I think is interesting. Anyway, what am I saying? They had a plan. There was an anecdote in this book, The Magic of the Primes, The Music of the Primes, that said that basically they would start each day out by writing, and this is 1920s, 1930s. They would sit down and write the goal for the day, which is to prove the Riemann hypothesis, and they would try that every single day. To be fair, I was saying, there's a danger of proving something that's not true. Most mathematicians believe that the Riemann hypothesis is true. That's what this book is about. That's why I'm trying to learn how to even say what the Riemann hypothesis is, which I'm kind of starting to get it. Like, it's, I don't know that I could do it justice. Like, I can state it, but it wouldn't make any sense, right? So what? Like, the zeros of this function lie on a line, right, on the complex plane, and they're all in any place where this function is zero. It's a great, and then it has something to do with the distribution of prime numbers, right? And then there's a bunch of theories hanging off this fact because it looks like it's probably true. Anyway, so in that case, they're spending most of their careers trying to solve a problem that turned out to be very, very hard to solve. So even if they're even if the thing they were trying to prove was true, they didn't have the tools to prove it at the time, and we still don't. As a civilization, we don't have the tools to prove it. So proving things is hard, and when you're proving something that is not true, and you are not aware of the fact that it is not true, or you're running up against something and you don't realize that it's hard, you can spend a whole lot of time. Like, one reason people who work on the Collatz conjecture are kind of like a little bit laughed at is there most serious mathematicians are not going to work on it unless they have like a serious, like something new has to happen to shed any light on it, on a topic like that, because many people have worked on this thing who are already familiar with a lot of tricks that mere mortals like me don't know about, and they put the time in to learn all these tools, and they've tried all these tools, and nothing, and hundreds and thousands of like professional mathematicians have worked on this stuff, and nobody, not hundreds of thousands, but hundreds and thousands, and nobody's made any progress. And it's what they know is that it's very, very possible to spend your career on something and not produce anything. I mean, I think Andrew Wiles spent like 8 years in his attic working on something, and only after those 8 years did he come up with did he announce that he had a proof of Fermat's last theorem, Fermat's last theorem. He was an exceptionally talented person. A lot of people have published so-called proofs that they've had sitting around, and they just don't have the rigor and they don't have the ability to tell that they've made a mistake, or as Neil deGrasse Tyson says, they know enough to think they're right, but not enough to know that they're wrong, right? And so in all of these cases, but even just if you make a simple typo and you think you're trying to prove something, right? You leave this thing off, right? And this is a whole new statement now. Well, especially here, right? Right? Like this is easy to prove. You move this over here. You move this little line over here. I say it's easy to prove. It wasn't easy to prove. It took hours to prove. You move that over here. I still haven't done this in me. And that's the difference, right? So the difference of one character changes, or the equivalently changing the direction of this arrow, and that takes something that is that I've managed to prove and turns it into a problem that now I've proved on paper, but I couldn't do it here. And why? Well, because I would introduce things, and the things that I introduced they're not the right path. And so I got away from the computer and I wrote down on this Kindle what I thought would be a proof, and it turns out like I knocked it out fairly quickly. And where is it? Like it's very short and it's quick. Let me just go through it. The proof starts right here, right? I guess I can't. Can I not draw on this? Doesn't matter. Proof starts here. So it suffices to say that there is a k prime in r.ks where k prime plus this is the formula, right? This is the exact formula for a term, right? So the term is that this is the k prime is this some number out of here, and we're going to use this number. So there's a prime such that this is integer division, so that k prime plus d prime times this number is the thing that we want to. Oh, this should have an equal sign, equals t, right? And then we're actually just going to plug in the same number that we used for. And so all these have primes on them. This is all saying that in order to prove, which I didn't even write this. This is informal, right? Like in my head, this was perfectly clear. I read it now. It's like, oh wait, I'm missing like all the context, right? So I'm missing this statement, right here. So I have this statement, and then in order to prove this statement that every term that was there is preserved, what it should say is that after I intro this, so I have this as my hypothesis, right? So that we say, in order to prove that this implies this, if this is false, and then false implies anything, so then it's trivially true. So you have to take this as a theorem, and you say, okay, this is true. Now I'll use it to derive this statement, and so then you say, well, okay, it suffices to show that this is the case, that a k exists, and such that the new d times this number gives that term. So the input divided by this, so equals t, and of course that would suffice. So we can write that number down, right? And notice this is not the statement I have, right? This is not the statement that I came up with, and I didn't come up with that statement until I sat down to write. And I was just thinking, well, I was approaching this as this is a hard proof. This is intractable. Look how long it took me to prove anything. I'm gonna have to do all this backward calculation and all this stuff, and I do, but like it was like 5 lines, and when I tried to do it on the computer, I couldn't do it, and I couldn't do it because I got distracted by all the other theorems I've proven. I got distracted by just I gotten used to the idea that I can just say apply term if, not apply simp term if, right, and that does something. That takes this goal and it rewrites it in terms of this, right? This is almost like it, right? This is very similar. So I mean that's close to what we're saying. So suffice. So we say show this. So it says exist k. I'm gonna call it k prime, and there's an x prime times r times n. So blah, 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 blah. So this is just a statement, right? It's already there. No, right, but it only that's only the right statement to show after you've done simp term it. Okay, all right, so we've done that, and then I went to immediately try and prove this. But I think also I did some other things. Like I applied the tools that I had rather than stopping and think, what tool do I need? I just reached, it's the old when all you have is a hammer, right? I have a hammer and a screwdriver and all this stuff, but maybe I needed I don't know, sandpaper or whatever, right? All right, so let's write it slightly differently. So this part is the same, such that so we can't assume that, but we can say suffices to show, and that rewrites the goal. So suffices that we can just argue about this k. We don't need the x. Then so that k prime plus d prime. So r prime dot d is d prime. Times, and then this is these are Iverson brackets. So n divided by z, such that n, and that would be written n divided by, we don't have a name for it here. We'll call it here. So I'm gonna call this z, and it's r z prime. We want z prime with hz, and it should be z prime, right? So z prime is equal to that m over z prime equals from phi. I'm not sure what the syntax is. I think it's from by, sorry. It's a weird syntax. Like you would think that would be equals n. And again, I'm going to change that name to t. Okay, so that's the statement that I think I should have. And then maybe we could fill that in by ESOP. No. Okay. Can I simp? So you have to actually produce it, right? I don't know how to work inside out. So I guess you still have to make this. But anyway, maybe I don't use suffices here for that work. But it like that's the goal I'm working at mentally. Do I need to prove this? Maybe not. I don't know that I need to prove this. I could just wipe it out and just construct the proof anyway. Well, but I guess I already have this. So use ks I. Right, I have it. Use or instead of saying suffices, we can just say have. right? So rather than saying that it doesn't matter that it suffices, we just have this fact, right? And then we'll use r.ks, r prime.ks. We're going to pick a constant in the new term, in the new break, such that n is divided by z prime. The index is n divided by z prime. All right, so we'll say we'll say set I is equal to, say I prime is equal to n over z prime, and set k is equal to rks of I. I'm missing the word by over here. I prime. And then I have to prove it that it's the right number. So we'll call it, we'll say sorry right now. Ah, does this work? This is legal? The syntax highlighting is a bit off, but I think that's actually legal. I think that's just a syntax highlighting bug. It's not a problem. Yeah. Okay. See, my mind just blanked out again. But I go here. Okay, so this I went off on some tangent. My mind is blank, and so to reset, it's like I'm looking around in my environment at what's on the screen. And it's like I'm just responding to that. It's like, okay, so that it's very easy to get caught up in a loop like that and not be aware of it, and just chase after something that's on the screen that is not correct, that is not good for you to be proving, because you're wasting a lot of time proving something that if you stop to think. So I think the answer is that you need to time box things. You need to time box things, and if you can't just do it on the computer in that time box, maybe what you do is you do it on paper, and maybe what you do is you write it on paper first. You go in with a plan, right? So you don't get sucked into something. Okay, so we said this, and now we're going to use that to fill in this goal that such a thing exists. Use k prime. Maybe this is wrong. Okay, so I'm going to call this I. I'm sorry, use k prime. Why is it not? Oh, okay, it did work. It did work. So the existential went away, and now I have to prove that this is. Right, so we say apply and dot intro, and then this is the first case is that we show that this is true. Okay, how do we show that? Well, reflection, right? You know, so that would be that's something like exact list mem of. So we have to say with hk prime. Now, no. It's like list mem of get, mem if get. So we say simp list. Okay, didn't work. Did it work? Okay. I prime. Is it r prime dot ks mem get I prime? No. Do I need this as well? Hi prime with hi prime exact ESOP. That's great. Okay, so Exact was able to close it after that thing from ESOP. Whoa, look at that. Is it because I didn't have this solved? Am I going down a rabbit hole? Maybe, I don't know. By Exact, how can I prove that? Like, div less than or equal, right? Like, I said what z is, right? So I said what z prime is. So I have that in scope. That's the length. That's this, and then there should be something that says like not enough. No, it's telling me my goal is this, but my goal should be this down here, but you can't see it. Yes, this is the goal. And over that, there's got to be some. Automation should find this for me. Like this is a step that automation should find. It's obvious, and every time I have to go over this. I have to have the fact. I have to have the fact. R prime H size. That this list is not empty. And now we can find this. It'll find something about division is less than provided I have this. But it doesn't find it. Okay. And so we have to go find that. We have to say list. I have one that says list mod length, but I don't have one called list div length. Mod length. I made this. And I bet there's one called div length. Div length. Nat mod. Say div less than. Is it true that div is less than? No, it's not true. I'm proving something that's not true. And I'm proving, and it shouldn't be that. It should, I'm using the wrong operator. Like the fact that like you would never use div here. Right? See, I did exactly the same thing. I wrote it down as this, and I was also using this is mod, whereas that's division, and I was confusing myself. Okay, so that's div. That's my problem. I made that mistake, and see immediately it turned blue because I could find it immediately. because I have this theorem in scope. All right, so we get rid of this. Can I register that with ESOP? Why? I don't know. I need to learn how to use ESOP better and simp and all that kind of stuff, because like this needs to be. I mean, granted, what I was just trying to prove was not true. So this is all garbage. I knew this was garbage. I wasn't going to keep it anyway. But okay, so now we don't need this. Now we can now inline, and then we're good. And then now this should be exact, right? Oh, this. Do I need that fact in scope? Exact. Like, this it should find this for you. This is so easy to. I had it a second ago. Mem if get, right? And I have to do it in the reverse direction though. So simp list, and we say backwards list mem if get. Okay, that worked. Do something. Do we say I prime? Use I prime. Yeah, see, that solved it. Simp all solved it. How I would say rewrite, and it solved it because it's rewriting this one at HK prime. Nope. Backwards, right? Simp, because it's a backward, right? That was it. Okay, so that's the end of the proof. Like that one line is the proof. No, it's not. Still not. And it wants to use I prime dot val, or we can also say up arrow. No, we have to say dot val. I prime has type now. Okay, show me again. What did I do wrong? Type mismatch. I prime has type n type in RKS length. Okay, so I fin RKS length, which is Z. Fin Z prime. What's wrong with that? Because you have to prove that mod is less than that mod less than n Z prime. R dot R prime dot H size. Does this have to be in brackets too? No. Like, this is tedious. I'm okay. Okay. This still not right? Exact HK, there we go. Can we even do this? Just use it, use I. So we didn't need the sim. Okay, that's probably just me being not having all the skills I need yet. Just not having practice. Okay, And I think I don't even need this anymore, right? Because now that I've proven that the... Yeah. Because once it's a fin Z, but it's not like in there. Oh, it is. Okay, I'm good. I've learned that this width, I had to ask about this. Say set width, and then when you put HK, it's the hypothesis that this is true. Before that, I was always saying, set this and then have K prime equals blah 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 by Ruffle, and then you like it was redundant, and I just had never noticed that you could do this, with word that goes with set. It should turn blue. I don't know why it's not blue. Okay, but this broke now. Use K prime. Like that. That worked. Oh, use I prime. Wait, is my goal already solved? Is use K prime sufficient? K prime has n type. Use HK. Exact HK. Right. So that it's use HK gives me that thing right there. Simp at HK. All right, so I need this rewrite. No goals. Okay. Well, that's kind of good. I okay. I'm proud of myself for typing that without, before it even caught up to me. Okay. Okay, so have I gone down a rabbit hole? I don't think so. I'm still proving this statement that was on my paper. I didn't say suffices, I said have. I'm still proving this statement, and this time I'm using the right operator now. This one it does need to be divided. Okay. Suffices just puts the reason for making this proof, so it swaps the order. So I'm just going to prove it, and then prove forward. But if you already have, if the the stuff that comes after this proof, after the here, like from this, where do I go? Right, so and intro. Then you can use suffices and say, okay, we're going to simplify the whole thing by proving this first. But I think we're just going to jump in and do it because it's short enough. Okay. Okay. Right, so I still had to say this. I'm just proving. I just said use k. So I've already defined k is n mod z prime. This I n mod z prime. A lot more difficult to write it in lean, right? But because I couldn't say this, right? I had to even make this statement to declare this thing. It took all these lines. Maybe I didn't need to define I. I think I don't need to because it just gets in the way. Maybe what I do is I put this here and I just stick this right in here. And then we make that a finite. But it doesn't like that, so I'm going to go back with the way that I know that works, even if it has a few extra variables along the way. So I'm going to call this I. But very soon I'm going to have to simplify it because I'm going to have to do calculations on this, but whatever. It got us through this part. Right? And then, so that's just that line right there. And then now I expand that. I'm expanding this line, right? So using this, now that means this. The goal should be this right now. That's it. Let me put this on this side just so I can do a sanity check here. Show k prime plus rd. So this is k prime plus rd, this d prime. This should be d prime. There's a prime missing here. N divided by z prime is n. I didn't put the equals n, but this is correct. Okay. And then the way we show that rather than saying show, we'll say calc. Okay. Good. We'll say equals. You say underscore equals. We're going to write the whole thing, so copy and paste it. I'll just do one side at a time. Or maybe so we'll say equals. I hope I don't have to have a proof at each step here. I'm gonna call that k prime is equal to I see. So I actually switched. This is correct. by this definition. So I didn't write this, but this is true. So I need to say, first of all, I can move all this out so we can have several topics about it. Okay, so and I want to set, I'm going to use capital K to be the list, equals r prime dot ks. R prime dot ks says z is equal to k prime length with k with hk prime. Okay. And I'm going to do the same thing for the other ones. So set k is equal to r dot ks with hk capital. Set z is equal to k dot length with hz. That I is equal to n mod z. No, we'll do it both ways. That I is equal to fin z. Maybe I should put these like this, side by side like this. You can see that they're equivalent statements at every step, just without the primes. Need that, okay. That should be. No, that's not fine. Okay. Okay. I'm mad about it. Like you feel like you're getting real-time responses, but you're not, right? Okay. And then this one, so z and z prime. I imagine that I will be doing a lot of this, right? Like prime and unprimed. This is a good candidate for a tactic, I think. If you want to make the style of proof that I would be, where you set up two variables on either side of it. But then again, maybe you could obtain all these like with some like generic structure. I might not need all these things. So what I'm actually arguing about here is not this term yet. I'm talking about this relationship between previous and post. Ks prime is equal to this. So I need to have this rule somewhere. So before I even get to that, we're going to say have Ks prime or rather have K prime equal to K, which is I've already defined here, right? No. So Ks I prime is equal to Ks I prime mod Z equals, let's just write the general rule. K I prime equal to K. This is primed to unprimed. So K prime I prime is equal to K I prime mod Z. And this is seemingly coming out of nowhere, but plus D, set D equals R dot D with HD. Set D prime equals R prime dot D with HD prime. It's a little redundant, but like maybe what I need is just like a thing that like lets you obtain all this at once. Although you wouldn't be able to obtain I, right? You don't know what maybe you plug this in and you would obtain all the information. Okay, that's the old D, right? Plus D times I divided by Z. I prime, it should have been I prime here. Or I guess I doesn't really matter, does it? This is the answer I'm going to wind up with, but I think maybe I don't need I. Whatever, I'll call it I prime. With I prime divided by Z. So all of this is to map the new constant to the old one. I don't think Aesop can find this, but equals. Exact. I have a theorem that's very close to this. And what is that theorem called? No, this would be partition depth. So this would be under partition depth. this. Can I hide this somehow? I can't hide this, can I? That's what I really want to hide. Because you can't see the goal. It's telling me I need to prove the property of I, so that's hi prime. I should write this the way I want it to be written. So we should say that A prime, well actually is this the exact same thing? Is it exact this? Ah, is this partition def? Oh, I see. So I'm missing this part. The exact formulation plus. Oh, here I wrote it backwards too. I wrote that backwards. Okay, so times d. And that's exactly this. Okay, so that's this line proved. This line is now proved. Now we prove this line, which is this right here. I can call this Z. Is this the same? Am I good? No. Okay, yeah, it's responsive. It's all good. No, something's not right. One goal. Why is it? That's too many variables. Too many variables open here. I need to be able to filter that better. I don't think this worked. This worked. Yes? I don't understand why it's showing. Is something in? No? 9307, one goal. What is the goal? Something is completely wrong here. Like even after sorry, it's like either sorry should be grayed out, the little line underneath. Right, something's wrong. Not going out of control. Okay, now that responded. Simple, right? It's still mad. Did I do something wrong? Have all these things that are in context. I gave you every one of them one of these ridiculous little. Such a mess. It's so hard to read this. Exact this should either close. Okay, what's happening here? Setting sync is on. the problem I'm experiencing is I cannot read this goal. K prime. This is what I asked to prove, right? What I have. K prime is equal to K, right? I'm just looking over here to make sure I define these right. Divided by Z at mod Z, I mod Z, I prime mod Z, that's right. This is what I'm saying. I prime mod Z plus I prime over Z times D. These are exactly the same statement. But exact this doesn't say that it's I mean, see, that's the problem with this notation. You have to, like, to get it into this form is really nice so that you can say it concisely, but then you're kind of screwing yourself. So if I say, okay, so if I rewrite HK, oh no, how about we rewrite it at the goal? So we rewrite HK, and we'll just bring these in line. Oh, this is wrong. It is wrong. There you go. Okay. Now it's exact this. By exact this. Right? Now you're happy? No? Still wrong? It's probably easier to clean up the goals. So rewrite at this. Oh, we have to reverse. Oh, we have to write them backwards. So we'll say okay. Oh, we have to say R prime, HR prime. Oh, do we not know what R is? We have HR prime, right? HR prime is this. R partition J HJ should so this should rewrite this. But it did. Okay, finally, it just slowed. And then same thing, like can I say simp at that and use the definitions? Simp HR HK. At this. No, I can't. I have to rewrite every one of these backwards. Okay. Okay. I see. So if I introduce a character, then I'm screwed. Okay. So that would be HR, or rather, that'd be H HK. I'm converting this line right here. See that? Is that? This is grunt work. This should be automatic. There's probably some way to do this. There's like something like rewrite let's. It doesn't do HK. R.ks. That should simplify that letter to K. Maybe because of this inside. Okay, so we'll do. It's just not doing anything. Give me an error, I guess. Okay, well that's called HZ. Let's just simplify that. It doesn't. Okay, well, how about we just, instead of doing it that way, we do it this way. HR, we say simp. HZ. I really think simp all should just solve this, right? Why is it so slow? Why is it? It did. No goal. Simp all solved it. Okay. That's all I needed. Okay. But it's just not, the UI is not responding, and maybe it's because I have so many variables. Like, this shouldn't be that hard. I don't get it. All right, moving on. So this line is solved. New constant to the old one. So we've got this formula now, and then we want to. I said suffices, but we want to show this. So that's this line right here, or this line right here. And we'll use that later. We'll use that. Okay, so now by this definition, so I got to give this a name, like just hdef for the definition. And now I'm trying to map. Wait. What am I doing in this text here? I'm saying I want to show this fact, right? K plus R. I even actually can call this. I can make this match almost exactly now. A prime plus D prime times N over Z prime, right? Is equal to N, right? That's it. Oh, except I call it N here. See, this should be called M at the moment. I need to standardize all these names, because I'm calling the input M, and it should be this should be M, and this should be T. Maybe I'll do that for just this goal, right? For just this proof, and then I'll fix all the others to be in line later. This might break something, but I'll fix it later. This won't break anything, because this is something I have to. Like, it doesn't matter what these names are up here. But I'm going to introduce this as T. So for all T's, then I'm going to introduce T a term. Oh, but I should use F2 to rename it. T. And then M HM would be N and HN, right? So this is now N, and this is HN, right? Because we're introducing this fact that our term N is T, okay? And this should be called N. And this is our term N is equal to N over, here I call it K when it should be called Z. And this is equal to D times M over Z, and this should be called N as well, N over Z. Okay, so N is the input, D is the delta, Z is the length of KS, and so this should be called Z down here. I see my camera just died. How do you do a subscript Z? If I can get my camera to stop being dead. Activate, deactivate. I don't know what happened. They killed it. Unless I turn it off and turn it back on, it'll. It doesn't usually happen in the middle of a stream like that. See? And if it doesn't come back on, I guess I just take my little head off the whole cam. Other camera. I can't stop. Activate, activate. All right, well, maybe it'll come back on, maybe it won't. Script Z. Oh, there it goes. All right, so yeah, usually in Lean here you type like something like that, and you get a subscript Z. Z. Oh, is it doesn't exist? I do not want to go through this. I just want to get a subscript. UTF Unicode subscript Z. Oh, it lacks. There is no such character. Okay. Okay, well. All right, well, maybe I'll change that. Maybe I won't use a Z then, if that's not possible. Doesn't matter. Z being the length of the list. Okay. Yeah, I thought you could do the entire alphabet like that. I guess you cannot. Interesting. I mean, that's only for a comment anyway, so it doesn't matter. Anyway, but Z is the length of the list for now. So this What I did was I rearranged these and close this down, make this bigger. Okay. Add the new constants to the old one. This is complete. This is again I've lost. I got distracted by something and I lost all context. So I'm having to reload. And very easy at this point to get tricked into proving something that's on the screen and not true, and not what I intend to prove. So I got to be very, very careful whenever I use this user interface to not get sucked in. All right, where's my other? Now I lost the other page. Give me a second here. 800 windows open. Probably put it in this one, right? Where the okay, so I'm proving this. I can't highlight it, but this line right here suffices. Instead of suffices, I'm just going to say have that. And the reason being, I don't want to have to prove this, right? So I just want to, or actually, if you say suffices, then you say if you have this, then you can prove the main goal. This is this. I'm just going to have this piece in here. I'm not going to worry about the exist part, right? Even though it's there. It's the way you, whatever. So because I define them, right? So k prime plus d prime. This yes, and this is it. This is Iverson brackets for meaning the floor, but this is integer division, so that's the same. And then I forgot to write equals t. So this is all the same. All right. So the way to have this is we're gonna. I'm surprised it says use k. Like it allows me to say that because use k does not have anything to do with this. Right? Right? So use k does not even make sense here. That was for a previous statement. I'm very confused by this user interface because if I say this should be the goal, and then and intro doesn't make any sense for this goal. So this should be giving me an error, and it's not, and so something is wrong. Right? Could be that I'm looking at the wrong line. That's entirely possible. Okay, apply and intros just doesn't do anything. Is that what it's telling me? All right, let's go back. All right, so I've skipped over these two lines basically. I'm just proving this part of this existential, right? So I'm doing a calculation on this, right? So calc k prime is equal, or I can just even, I don't even know if I need a constant for this, or just k prime, right, is equal to k, big K prime, I prime, right? And that is by the definition of HK prime, or that just equals HK prime, by HK prime, by exact HK prime. K prime that's the definition of it. Oh, because I didn't say it exactly that way. That's K. Oh wait, actually that's wrong. See, that's why I wanted to use it. So this should, that's HK. Copying and pasting, right? why all this should be automatic. Now what's wrong? This is like 10 steps behind me, isn't it? But it says it's broken. And I broke that proof by doing that. But this looked correct to me. I believe this is okay. Maybe I broke it because something was wrong here. K is HK. K prime is this, yes. D is this. D prime is this, yes. D is K length. D prime is K prime length. Yes, that's right. K prime, K, yes. I is T of Z. Oh, duh. I prime, yes, there's a prime there. HI, that's all right. K is exactly right. K prime of I prime, that's correct. It doesn't like this. Fine. It doesn't like this because this says that okay, this is actually a valid problem. This is a valid practice. So we can get rid of this. This is true. This is still true. But I have to prove that it's true. Why doesn't it like that? R size with HI. This should be valid. The index is valid. It should that is a A is defined as RKS length. Yes? Good. Okay. Z is the length of K. Yes. I is a finite number less than or equal to Z, or less than Z. And we know that it is equal to T mod Z. That gives it the property that it is less than Z. Okay? But why is this mad? Why are you mad at this? Failed to prove that the index is valid. This is exactly right. Oh, no, wait. There we go. Okay, and I have to prove that. Okay, so that it's mad because I mean, what was there was true, because mod z is the same as just like it's already defined as mod z, and here it's you would have had to put the operation in again. Okay, but now why is it mad about this? This is what goes in that slot, right? And it worked a minute ago. Oh, this is actually I dot prop. I don't know why this worked before. Possibly the partition def takes R prime. No, it takes R partition by simp all. I'm a little confused by exact what. Surely this is in scope, right? Takes what? By z prime z length. That's exactly right. So it takes r the rate, j, j, h, I prime less than the length, right? And this is I prime dot prop. There we go. Okay, that it took it. I'm surprised you can't just say exact. I bet. I want you to be able to say that. But no, you cannot. Okay. Okay. Okay, back over here. We say k prime is equal to k prime by exact. Yes, exact hk. That's right. That's exactly what it should have been before I realized that my okay. And I'm just going to skip this step. I'm going to have this, and then we're just going to say exactly this. Oh. Actually, really, I could say calc. Probably start here. Have k prime is as by equals hk, and then have this. Just put all this right here. Okay. And then just not even have that stuff. Right. Okay. And then the next step would be what? And that is hi prime. Hi. See, now it wants a proof, doesn't it? All right, so maybe what in order, like, because I have to provide a proof that every version of this, if I put it in brackets, is the same. So what I need to say is have I prime is equal to n over z, n mod z, by the following logic, and I'll just do the parts that's like in parentheses over here. That's not right. What I want to say is I is equal to I prime odds. To I prime. Dang it! Like this made sense in the right, by this formula right here. I went from I prime to I. Okay. Okay, so I guess this is already done. Right? This already simplified everything. So this is already done. This step got done for me because I is already this. So this is actually fine. Okay. Plus D times I over Z with the implicit floor here because this is division. Okay. We can just say this is K, right? We say this is K by HK. That's not what I did in this proof by reverse of HK. I rewrite this, right? Yes, no? Yeah, that's okay. Plus I over Z times D, that's the same? Yes? But why are you mad? Calc tactic fail has type. Okay, so it's just mad that I haven't gotten that far. Can I put that there and then it goes away? No. Maybe what I'll do is I'll just write this. So K prime calc K prime is equal this is true. Okay, so this step. Now people are watching now that I'm struggling and being stupid. hello, hello, people watching. Okay, welcome. I'm very close to a proof here. I'm almost done. But on paper, this made a lot of sense this morning, and then just trying to convince Lean that it's made any sense isn't just not working. This is what I just derived. I got this formula. This works, right? This is already there. I have this formula. I have this line. Like I'm starting from here, like I guess I should start from the very definition, like this. A prime plus d prime times n over z prime equals t. This is by this is the ugh. This is the definition of a term, right? So have equals term def r prime term underscore def of n, right? And then we should get this. And it says so many things in here. Oh, term simp maybe? Okay, so we obtain these things rather than obtain ki. We're starting with the term that we have, so we can just obtain it, right? Boom. Okay. RK of term. That actually came from somewhere else, but we have that. And we should call this term n equals t. Term n equals t. So we'll call it ht. And now we're actually obtaining but it's not called hm. N equals k. All right, so these are named weird, but this should be t, right? So it's h. This is my h. Oh, okay. This is hn. The hypothesis about n is that term n equals t, and this is ht. Yeah, I should. Okay. So we're good here. K is a member of KS, of K's. I is that thing. So I is less than that number. Finite in that range. And I is the particular one, n divided by, I didn't call it z, but that's okay. And we'll say the only thing I need to set now is z is maybe but I don't need I because I've got it here. I've obtained it from the actual formula. And just to be sure that it is T mod Z, I is says N. Right, that's correct. Yeah, why did it say T mod Z? This should be N mod Z. N mod Z prime. Now okay, how much? That didn't affect anything because I didn't use that fact yet. So we have K and then length of K. So we have these things. Everyone left. I don't blame anyone for leaving from this. It's terrible. Absolutely terrible. But I will finish this. Yeah, when I'm programming, like I know what I'm doing. And, like, people watch or don't watch, it doesn't matter. But here I'm just being. I feel stupid sometimes. All right, and this broke again. Okay. N mod Z prime. Oh, Z prime. That's I prime. No, HI should be. Yeah, that's right. I mean, isn't that not exact HI? Exact HI? No, again, it's not simple. What is wrong? Why can't it show this fact? N is equal to R, get I. N is, that is how I is defined. N mod RKS length. I have an I1 here. Where did I go? I feel like I is in scope when it shouldn't, like the old I is being defined right here. Let me just double check. Why is this broken? Like right after this line, we have I is n mod RKS length. That is correct. K is that, right? And then when we say this, do I even need these? Like, can I just say this? Okay, I had this exactly. I know my head's in the way. I can't. Maybe if I make this bigger, I can scroll. It says people are talking to me, but it says there was a chat, but I don't see anything in the chat. I wish there was something you could use to just make it like fill in, like reverse simplify. Is there rsimp? Like to simplify this based on all the. Right, but let's just read it line by line. This is correct. A prime equals RKS I prime. Oh, that says I prime mod RKS length. Oh, so yeah, right. So I have to show have I prime is equal not to I. No, we have to say I is equal to I prime mod something. Mod what? What is it equal to? I prime mod Z. So say I is equal to. Yeah. Can I work backwards? No. I prime mod Z. We start it like here. Calc I mod Z. Maybe I should go it in the other direction. Then I have a simplification rule. Equals I. Oh, really, it's by simp, right? Okay, by omega. Okay, so I don't have to prove it. That's just true. right, so now this works. Yes? No goals. Okay. Now, why is this mad? Because I changed the T to an N, okay? I did that like 800 years ago. That's so frustrating. I kind of think of my... What is this missing? Should I be looking at this? Should this message be showing me something? Is the problem that I'm having that there's so much crap in this thing that I can't see what it's telling me? No, that's not the problem. Omega, why is Omega poop? God dang it. This was working a second ago, or at least it didn't break. I need a fact that says have z prime is equal to z times j being the number that we're partitioning on. And that is have, so we'll call it by, or equals by. And that is length partition equals length partition equals r length partition j. Hj. and it winds up being j times this. And then we say simple probably. Okay, this should be easy enough. We rewrite hi prime. Is that not what hi is? Sim? Why is that not right? I need some fact about uh, hi is that I equals n. Z by Ruffle. I dot value. I.val. Oh, I can't see that. Maybe it's a bad idea to use these little terms. .ks.length. By exact HI, right? By HI. What does it think HI is, right? HI is this. But what is this? Where does this one come from? Do I create an HI somewhere else? Is there anything below me creating this nonsense? I create HI right here. Hmm. Maybe Lean was upgrading in the background or something, and that's why everything's been so wonky. Like this is just not responsive. Like, what is this nonsense? Is this did okay? This did everything I needed it to do except for respond in a timely manner. Like this is ridiculously slow. I keep clicking here to try and see what. Okay, so here HI is defined easily. So why? At what point does I go away? Oh, okay. It's here. When I do all these sets, it's rewriting that somehow. What if I put it down here? And I have a new K here. Maybe by overwriting K, I was screwing things up. Yeah, now everything's working. And I don't have all this little weird stuff in here. It wasn't that. It was the fact that I defined K again. Let's revert that. This is perfectly fine up here. It doesn't matter where it is. We can just put it anywhere. But I wanted to use this so that it would rewrite things, but I shouldn't have used another K because that screwed up my situation. Okay. Does look like I defined another I here somehow. We'll see. Let's delay this as much as possible. And just put the Z and K down here just to rewrite the terms I want. Right, so K, Z, I. And this needs to go above that. Okay. Still saying K length. Okay, that. I still have an I prime or an I1 or whatever. Where is that coming from? Looking here, it's still here. I'm looking here, it's still here. Not here. As soon as I do this, not here. Let's everything's churning, so I gotta stop it. It has to go to the bottom of the file before I can really, before it becomes responsive. Okay. Now on every line, what should happen is on every line, things should change. Over here, as I move the cursor around, it should change, and it's not changing, and it's not showing me the right information. Also telling me I have a Decker script. It's not just space. Like I don't feel like I'm fighting with my proof right now. I feel like I'm fighting with Lean, right? Is it when I introduce K that this shows up? Okay, so this causes something bad to happen. So let's not use these. It's kind of unfortunate because it was so much nicer to have it this way, but. And now we don't have these things in scope, so we gotta call this K. And this is r.ks.length. Now it can't prove this. But we have I mod RKS length, so if we simplify that, we should get I. Simp this, or we'll say rewrite. Let's say HII or HI prime I. And that solves the problem. It's right there. Why can't you see it? All right, so okay, I can't do something after ESOP fails apparently, which I guess makes sense. So there's still goals to prove here. Terrible. The problem, you change something up here, it breaks everything that you've already done. You have to do it over and over again. I don't even know what's happening. That close? No. What is it asking for? Like, why did this work a minute ago and now it doesn't work anymore? Oh, we don't know what K is, right? No, we do know what K is. All right. That works, yes, okay, but it doesn't give me errors. And then does ESOP find it? I get rid of D. R.D. So okay, and ESOP finds it. See, like it didn't give me a little squiggly line under here that says I don't know what this is. I didn't turn this on. But how many terms is that? How many? I say false. How many things does this break if I do this? Okay, off. Look how many of that break. What's wrong with that? Complaining about a token that's not there. So you have to make that one implicit. Okay, so this is why I don't have that thing on. I'm not going to do this right now. I should have had it on from the start. Oh, come on. What's... It's frustrating. 6 o'clock in the friggin' morning. What I should have done, I should have recognized that when I see functions everywhere, All right, let's get rid of this too. Okay. The only problem now is that that I don't have a sorry here. I still have the help in here somewhere. Line 9. Yeah, this is like ancient. Start the file. This line is gone. I have not had Lean behave this crazily for. I wonder if it has. I wonder if it auto updated or something, because I saw it. I don't think I didn't ask it to update everything. Right? It just seems to have updated things. I didn't know I was on some like auto update schedule. That could be part of my problem. 4 hours at this now. It's ridiculous. At least the words are turning blue. That's good to know. Two of those hours were me talking, but like this should not have been. Okay. All is proven easy. The only problem was that I had a D instead of, I didn't have a word defined. If I change this to D, it's going to break and it's going to show me like a bunch of functions over here on the right hand side. Right, see, it says fun everywhere, fun X. It doesn't explain to me what D is. I'm surprised I don't see like fun D. Where is, shouldn't this all be wrapped in something that's introducing a D if D is not. All right, we're good now. Okay. Too much? Okay. So why do I believe that's true? Because this is the definition of a term. I should have a fact in here. But again, I'm responding to this and not looking at this. So have I? That's the same. I have to construct this term. And if I can do that, then that's the end of the story, right? And then now I go back here, and then I can say use k prime apply and dot intro, break this and up, do sub goals, simple. That didn't fix it. I prime k prime is this, and so that not exact question mark is not supposed to solve the goal. It's supposed to. This is buggy. Something is broken. Yeah, that's what's supposed to happen. It's supposed to say, hey, I couldn't find it. Did not close the goal. Okay. What is the goal? The goal is to show that k prime is an element of r prime.ks. Right? Show simple. Okay, you don't have to simple. It's exactly this. It's exact. It's not exact. It's not exactly that, but like you can derive it from this. So Aesop should be able to find that. Can't. Why not? We say convert. I haven't learned how to use convert yet. I keep trying everything, thinking that I'll get there. Convert HK, and it's supposed to like give you some goals to. Okay. That looks pretty. Okay. There we go. That's super ugly, but are you freaking kidding me? Look at that. This is broken again. It says it's never executed. No goals. I don't know. That's ugly, but whatever. All right, and then the next goal is what? So we have to fill in a value. What is that? We're going to use this right here. Use n over z prime. I see. Earlier it wouldn't even let me use. I wonder if I have to. Huh? I wonder if the parens had anything to do with that. That's fine. It wouldn't let me. It wouldn't let me introduce something like this before. Maybe because I was using brackets for k whatever. Painful. Maybe I'm just not good at this. I'm not good at lean yet. I'm fighting with. I don't even know. And that was exactly this, right? Is that not this? K prime. Oh, I have to simplify it. Uh, Something's missing. Okay. K prime plus n over z times rd equals t. All right, well, let's just write it the way that it wants it to be. And then we say exact h. Oh, it still doesn't like it. I see. So use can see that goal, and so I don't have to give it a name or anything. Okay, I need the colon there. And then that's the proof. So I just have to I'm down to this one line here. And on my camera it died again. Why did my camera die? Because it got disconnected. And now the screen's gonna crash. Okay, it did not crash. I turned off the camera, turned it back on. Here's me. You have to zoom in or else it won't. Green screen's not big enough. Okie doke. All right, so how do we prove this? This is the statement I want to prove that's right here, right? Where is it? That's why I wanted the syntax to look. Maybe I should have just rewritten this by hand to make it look better. Yeah, I zoomed in too much. We have this part. And now we want to show this. This is the thing I'm proving now. Really, these two terms should be backwards. It's k plus d times something, not something times d, but whatever. It's because I wrote it differently elsewhere in this file. I should be consistent about it. But I can clean that up much later. All right, so here's where I'm using use k prime I've got. So this is the translation. Can I change this word to k prime here? Okay. So I have a fact that something equals t. Yes, I do. I have the fact that term equals t. So I have the definition of term. I have ht, right? Term. Okay, so I can rewrite from term. So rewrite at term. Sorry, not term, ht. Conv at ht. And we'll do sim. And rewrite. Sim is not something you can do. Do that now. I thought that was something you could do. it eq.sim? Eq ruffle? I could have sworn you said you could say sim. Alright, whatever. Oh! Well, okay. I mean, that's what I want. HT is this. So I'm trying to make these two things the same. Like this should be a straightforward calculation. T equals. This is my assumption, right? I'm starting from this. All right, so the answer to this is simp all, and then simp with the how about we rewrite term as this? So rewrite. Wait, is this my goal? Is this the goal I'm trying? No. I feel so dumb right now. Okay, I'll do this backwards. This is what I'm trying to prove. Well, except I'm back here. Is this what I'm okay? So I'm starting from. Is this basically this? I times. This is what I is. I prime is this. All right. So we're going to do this individually. Really clunky. Like this right here is this. I plugged in I plugged in N. Maybe I can do this. Have I is equal to, and I could have sworn I did this a little while ago. Equals N over T. Sorry, N have I prime equals n mod z prime. Have I prime equals I. Yeah. Yes? Good? Okay. But what I want to do is I want to slowly convert this term into this term. I should write it explicitly. I want to start up here. Because this already works. So I should say, hang on. There we go. So here I don't have the proof. So now I need to prove this. So what does it want me to prove? It wants me to prove that this is that. Okay. So rewrite t as this. And there we go. That's the goal I want to prove. All right, so I can rewrite kdef, rewrite ups hdef. Wrong with that? Instead of hdef, we'll say rewrite hdef. Right. So what I'm doing here is I'm taking this k prime, plugging in the value of k prime, right? Did I just say simple? I don't see that squiggly line going away yet. Oh, what is it leaving with? Okay, so we won't do the simple because it expands things instead of shrinking them. So ugly to look at. But we're going to rewrite, right? So so we'll say have I prime mod r.ks.length which is this, is equal this is I prime mod z equal n mod z. Sorry. Motive is not, okay, come on. Simp h0. And then we should be able to rewrite that as k, right? But will it unify? What if we said this at h def? Right, so we can then there'll be at least on two different lines. If k prime maybe this is a calc proof, right? What do I need to prove here? I need to show this. And if I do this much, everything's solved. If I get there, I'm good. We'll say calc t is equal. And now we're trying, okay, so now I'm trying to work it this way. I have this fact. What is the fact that I have, right? I want to show, this is my goal, right? Solve that goal and I'm good. Okay, so this is what I need to prove. This is my goal. We're going to calculate it. What do we have from t? What do we know about t? We know that t is this. Now t equals this by ht. And just so I'm just doing a sanity check here. If I do this and I say by sorry, then I'm good, right? I have to say y first. I have to say y equals hk, right? ht, that's what ht is. Right. And then if I do this, I don't need that completes the proof. So the calculation can complete the proof. Okay, so I'm working backwards now. K plus dn, K plus d. Yes, this is correct. This was wrong. This is correct. And so now we're going to replace I just got to go through the motions. Okay, so we reach there and then we say that. Okay. We go step by step. All right, so we fill in we're going to replace n with the following. N mod z, I'm going to say j times n mod z, and we're going to rewrite this in a second. Plus j times n divided by z times j. What is z? And now we maybe it makes sense to use these in the calculations at the end. When oh, come on. Oh, this is not HT. Okay. And there's a law that says you can do this, and if I don't have it exactly right, it's not going to work, but it's called like mod mod add div add mod n times m over n. Okay, so n times so here n is j. Okay, so we're going to write this we're going to write this in parentheses. Okay, so we're starting with n and we're going to get so that's unfortunate. Is that right? At div mod add. It's not right, but m over n say n over j. And that's not right, but Setting unknown constant at div mod add. Div add mod, sorry. Okay, that worked. Why is there something broken beneath me now? No goal to be solved. Right. That's right. But why is? Oh, it's because of this. It's an implicit argument. You know, it's like a implicit argument. I'm not using that fact. So if you don't use the fact, then because it's implicit, you have variables. If you don't use the variable in the thing, but I think I will in just a minute because I've used J here. So I'm not going to worry about this. I think this will write itself, and if it doesn't, I'll fix it afterwards. But I think I'm going to wind up using something like this because I'm using J here, so it should be. Wait, does it not know what J is? It has J in here, right? Where's J? J is in that, right? And HJ is here, so I'm using that. I'm using it. I don't know why it's not. Why did this drop out of it? Oh wait. It wants R prime. And then after R prime, it wants what? Is it because it's not making use of I'm not going to worry about this right now. As I'm changing the definition, it's causing this to change. As I'm changing the definition here, I stopped using something. Like if I say if I say have equals HR prime, then yeah, then the definition fixes. To do, remove this line. Okay. And it's because these you know, they rely on different things. I just don't want to break something, right? I'm so close to this. I'm like lines away from this. Okay. So backing up here, we've done this line, so now we're going this line. So what's the idea here? We're going to distribute r dot d over this. So let's call this set d equals r dot d, and then we can call it boom boom. Okay, so we have this. We're going to distribute this across here and get the d over here. Does it matter? I don't think it matters where it doesn't matter in my proof where they go. Is this allowed? I'm gonna say omega. It doesn't matter to me what the proof. God, just. I'm gonna try this thing. Import. I don't know if this is gonna work. I think it doesn't. Doesn't. Why is this divided by z not in my proof? A plus dn. Well, this is what I start with, right? All right. When I wrote this, I have it in two directions. So I'm starting with t. These are two different things. This is about t. This is about t prime. So I'm trying to show this, and I'm showing the equality between these two things, right? Is this bogus? They're basically exactly the same, right? So I have this. I have this fact right here, which I did write down correctly. Okay. And I want to show that this fact exists. I'm showing what? What am I showing at this point? I'm showing this. That's all I have to show. That t and t prime are the same. But explicitly t prime. This is t and t prime. They're the same number, so I'm showing that they're equal. That's the next step. I have k prime plus n over z times. I'm on this line right here. This is what I have, or this is my goal, right? And I should be able to transform this goal starting with here. So in this one, I'm actually working backwards. So let's start with this one. Calc this. Let t prime equal this. They set t prime equals this. And that should change the goal to set t equals t prime, yes. And so show t equals t prime. And we can just, we don't need it. So now t prime, well, now I can go in the direction I want. T prime is equal to this. is equal to D, and that's REFL. That's how it's defined. How it's defined. You gotta give me that. And this is not right. This is where I want to end up. You gotta give me this. This is why is it? It's just this is the goal. I say sim. Flip that around. Oh, but I do want to argue in that direction. So we're not going to flip around. This is T prime, and I want to reduce. I want to define this as T prime, and then argue that it's equal to T. What I'm expecting to happen? Yeah, this is what. Like I'm expecting it to rewrite the goal in terms of. Okay. Like it's supposed to do this automatically. Set is that's the whole point of set. It doesn't do it at the goal because it's r prime d. R prime d prime is equal to r. I'm not going to do that. R prime dot d is small enough to write. Right now the goal unifies, and I have to show t equals that. But I know what t prime t is, so let's write t is this. Hopefully that should just let me write that. So we have to say subst ht. Okay, so we're going to rewrite that, and now the goal is this. That is what I'm working towards. I don't know if I'm going to make it, but we'll see. So from ht prime, we have this. That's true. Okay. That's this line. K is this plus this line right here is what I'm looking at. This line right here. These lines are false. They're actually, I was working backwards because I was confused once again. So and we want to end up at this line right here. Sorry. Okay. So the line right above that line, this is that line too. This is the same thing, except I called it D instead of R dot D. Call R dot D. Okay, so that line is redundant. And this line is I don't know yet. Somewhere in between. That's this line right here. Let me move this over. Give me a little space to work with so I can see what's happening. And I don't get confused about what's a proof and what's a A plus D times N over Z. That's where I want to show. And this is a way of rewriting that. Okay, so we have T prime is equal, I'll put it right underneath each other so we can see the parallel right here. This is what, It's fine. What do we know? We have undo, just undo. This is not immediately true. Like this. Oh. Wait, are you telling me that? Okay, yes, that should be easy to switch. And I'm going to rewrite this as r.ks, r prime.ks, I prime plus rd times n over z. By a sum. That solved the goal. Okay. So these just unified, and the other one solved. I didn't want that. I wanted to use this rule right here. Right? Yes, because I'm this whole thing right here is this term right here. Everything, this plus sign is this plus sign. This all is this. I'm expanding that k, right? And that's by this definition. So instead of that, we're going to write. Let's call it k prime. Let's just keep this k prime here. So we did a trivial adjustment here. plus this stuff stays the same. By simp hdef. It's some specific set. This is our h size. Okay, so now it's complaining that I just didn't unify. Left hand side is something, previous hand side is something else. Hdef, what is hdef? Hdef is this k prime. And we're going to call this r.d instead. Okay. Okay, this is giving me some hope. We did this expansion. We have our little terms. I actually think we can say let me just generalize this a little bit. Say, I'm going to say h. Just call hi for index. Sub h sub I is lambda I for any index I mod z, like that, right? What if I take this out? This line should fail, right? Are you telling me I don't need this? That's crazy. Okay, so that's the same. So it seems like if this fails, then this fails to unify. And it says it doesn't know how to synthesize the proof, even though it's the exact same line. Or if you say by ref, okay, so interesting. Okay, so I want to replace that I'm with n mod z. N mod z prime by sim. No, if I rewrite hi prime, right? Hi prime. Or we don't even need it. We have this, right? Wherever it went, hii. We can just jump directly to hi. Hi dash hi. I don't understand why it lets me do that. Why would it let me put an X here? No, it doesn't. Okay. I'm just going to try and jump all the way to this. This is what I want. Like that's what this says, right? Is I. Okay, so we're going to rewrite h I dot I. You can't rewrite it that way. You have to say sim. Okay, that looks promising. Because that would be hi. That's not what hi said. Hi is that this is active. Okay. E hz with hz up here. Now is it solved? Solved. No goals. Okay, but it doesn't know how to synthesize this. But this is solved. All right, so maybe this is already in context somewhere. I don't know why I solved it the first time, but not this time. This is hi thing. Yes? Good. Okay. I know something about this language. So we have to prove this by modular or mod arithmetic, and we'll say hi sub. Okay. Cost hix for index. Ix. For ix n. Yeah. You have to prove that it's a valid index, and you're not, right? You just put that there. But it can't find that. Yeah, it can't find the function. So you can tell it to look for a function. Ix. Or just give it a name. And here we can also write that in that same step. We'll call n divided by z. Same step. I guess we have to choose which one of these is true. Left. Yeah, that's a theorem. Right? To say that something. What do you want me to say? Say. Oh, it's not a theorem because these are not the same thing. Because with that, there's an apostrophe here. But it happens to be true because this is a multiple of this. N mod this is the same as this. Or rather, this is a multiple of this. So n mod something divided by that something is 0 in natural numbers. And then n mod some multiple of the something divided by the something is 0. All right, so I'm so close. This is the stupidest thing. I don't even like this anymore. I'm gonna go be a farmer. I'm just this is all. It's just hard to translate this back and forth. N divided by p. P. All right, let's rewrite the z prime and rd prime. We're going to call this, this is RDJ. I think we spell it like this. This is z times j. I think we say we spell it like this: r dot d times j times this. Let's see if it'll make it into it. All right, so we got to rewrite this piece by piece. Wait, no, I'm being stupid. All right, so we're simplifying by the definition of r prime dot d. How about by, do I have that in scope anywhere? It's implicitly here, but that should exist somewhere. Simp even simp. All right, finally we're using that thing, so I don't have to use that anymore. Oh, come on. There we go. That's all. And now that I knew we needed that thing, so I didn't want to like rewrite it to not use it, right? Oh my god. This was a plan on paper. So hard. Not hard, it's frustrating. Like it's tedious. Like there's things that it should do that it like this is all gonna simplify away. Call this H D prime. Now maybe sim just gets this. We rewrite by HD prime. And Z prime. HZ prime. And then have Z prime is equal to R dot KS length. That is H. But you say it by assumption, right? Okay. That work. Unsolved goals. What's it mad? What's it mad about? Look at that. This line's broken again. Why did I move on if it was broken? It looked like it was fixed. That's this thing up here, right? HD prime. I need the J on the other. No. This is not. So it's HZ prime. I need a HZ. What is it actually saying? R prime dot ks length is equal to. This is called the. It's called partition length. I have to first show that you're not. Okay, so have. Really are. I did put all of them in there, like H size, and I keep taking them out of scope. I don't know how to use convert. This should be a theorem. Okay, this is something I've already proved. Oh, partition length. Length partition? I'm just tired right now. So we call this H D prime D. Yes. And then we want H to be, by substitution, H Z prime Z. And that was it. Okay, so we just had to simplify by those things. Okay, it's so tedious. A lot of this could be done by automation better if automation can find it. And maybe I'm just not using the automation there correctly. Oh, this is still complaining about this line up here. So maybe we can change Z prime Z. This is a theorem. Maybe it's not a theorem. What did I change there? I need to rewrite this so that I need to get rid of that J. Mod mul. It should be called mod mul. Is this not true? Or is it just... I could have sworn this line was working a minute ago. Don't know what I changed. Maybe it just never worked. I thought it was passing when it wasn't. But clearly, like, that seems very true to me, and maybe I'm just tired and I don't know what I'm doing, but like, that seems true. I would think this right here. Oh no, that wouldn't be. Hang on, maybe when I picked left here, maybe I picked the wrong one. No, I can't. It's definitely left. Maybe I wrote something wrong. Okay. So I believe this. N mod the length times j. This is talking about be very, very clear. This is left the small thing, n mod this. So this is not true. This is a big number. This, you would not expect this. Did I use the wrong symbol here? Did I get to include something? I'm rewriting D prime here. Here's I prime over Z. Maybe I'm not ready to do this step yet. Like this part of it seems okay, and the rest of it does not. Oh, that's fine. That was something I was half. Maybe I can. Maybe I wind up simplifying this later. Is this K right here? This is K. We can shrink this down considerably. Right? No, we gotta do this, and then we can switch this to K. Okay. But is that K? Yes. Not quite. And my Z is I, so we've gone from I prime to I. We have to say H. HI. H. No, that's not it. Well, if this is true, it should be easy. Not true. You have a typo in the. I should be n over z, so we should have hi, and it should say it's n over z. I prime. Hi is this, so I have to. I do have HZ simplified. I val. Why don't those unify? RKS n mod RKS length equals I. HI I is equal to n mod RKS length. What do I have to say? Convert. Oh, RKS get I is. These are not true. I don't expect that to be. Something is wrong. Something is typed wrong. Put it back here. I don't want to say. I don't want to break the rule I already have. That whatever I already have. Okay, that was easy. And I think I can drop these parens in that line as well. Without having to explicitly invoke. And I think I can get rid of this j times this over here. Oop. Didn't do that step. But can I put this here? Nope. Okay. Let's get this r.d times this and remove those. Good. Yes, okay. And then, oh, no, not good. Good or bad? I just want to rewrite it. No, that's some of the things I can rewrite. What? Do I have to do this? Okay, that's easy. So we can say simp here. Okay. Sorry. And then we can put this whole thing in parentheses and remove that other like this. And that would be a not mul add in reverse. What am I doing? So this is associating that way. So I have to put this in parentheses. Then I not mul soak. Rewrite not mul. And then here we put. Didn't I just try to do that a few minutes ago and I couldn't get to it? That's a lot of parentheses. Fits. The logic is I've got After nat mul com, not seeing anything happening. I did something wrong. Let's try again. What I want to do is switch these two things around. Plus r.d times this, right? We haven't done this yet. Do it in 2 steps. Ah, okay, I see, that's the problem. Gotta put this in brackets. Nat mul soak. Okay. And then we can extract it. Times, and then put this over here. And get rid of this. And put this at the end. Everything balances. I need nat add a sock. Nat add also. Is it the order I'm doing them in is not the order it's doing them in, and so it's getting confused. Right? Possibly. I have to do them in the exact same order, right? All right, so oh, that swapped a big thing. That's not what I wanted. That's what I wanted. First do that, then do that, and then what's left? Not all that, right? Do I have 2 lines that are the same? Yeah, these 2 lines are the same. If it will not let me do it, I'm going to be so upset. it doesn't let. I'm testing out a rewrite down here to see if it's safe to do it without like introducing them, because I don't know. I don't want to like accidentally do it. And then we can delete these brands. And I think I can delete this. Or no. Yeah. Okay. That one's not quite right. Okay. I'm close, right? I think if I make this substitution, I can do this. Right? So the substitution is now to put this in here. N mod z by omega. I feel like that's a. Oh wait, is this failing because I don't have the J in there? Right by. Yeah. It hasn't. It's failed. Now you put the checkpoint after the goal.
Is this true or not? Wait, I prime is what? I prime is n divided by. Okay, let's get rid of these checkpoints. Sorry, that didn't help. This is true. Like this I believe is true, right? By hi prime, right? By rewrite of hi prime. And give me a. I did prove this twice. Redundant. This is gonna break this line right here. So that was H. Maybe.
All right, why is this mad? We call it calc step or something like that. I'm trying. What convert does is it tells you what the steps are to convert to gold. What is it? Oh yeah. Never mind. I prime. I should have a thing called I prime somewhere. Right here. N mod Z prime. I should be able to simp that with simp hi hi prime. Oh, I closed an extra paren, right? That's good. Let it catch up. Okay. I'm gonna close this paren right here. That's good, right? Everything's good. Nothing should freak out about that. It's just parentheses. And in here we say n mod z prime. That's what I thought I had typed before, and it's not. Okay. And then we're gonna simplify hz prime, which is z prime is r prime dot. No, we want hz z prime z, right? Which is some up here somewhere. Hz prime z times j. So we get a j in here. have to say left. Okay, I just introduced a typo somewhere. This is good. It likes this. This is fine. Everyone's happy with this. Z times J, right? I see what it's asking for. HC. All right, once I simplify that, now it's good. Okay, so it needed that information to let me do that transformation. Painful. What can I do with this? I feel like I had this exact same situation in the in the previous proof attempt. It took me hours and hours. No. Okay, is this true? All of this must be true. But is this jump true? Is this jump true? I'm down to one line, right? This is the only line. This is the only line I need to prove. for this entire project. This is the same thing, right? I got to show that I can convert this line. Yes, this is what I want. Not mod. Okay. Now divided by n, right? I can cancel these two things. N times k divided by n, right? I can convert this to. I knew this was here. N mod j. Yeah, N mod j. Okay, right? Yes, this is the case. So by exact, and you should find this thing right here. Nat mod mul right div. No, I didn't. It's not quite right. Equals m over m mod n over k. N divided by. Man, I can't even just. There's too many letters, and they're all the same letters I'm using, but they're not the right order. Okay, so we keep the n here. So this is not the same pattern. We have k here, so we need this pattern right here. They're about both exactly the same, but we're going to have this on the top, core side. Right, exactly the same, but just with the switch. Okay. And we have to write it like, okay. So as we convert it around, we're going to get n divided by n is z mod k. And it should find what I just. I think I'm dealing with invisible parentheses. I call it K, it's J. Right? Oh my gosh. Does this simplify? Not going to simplify. But there's a rule similar to this that simplifies. Nat mod cancel. Nat mod cancel. Like, I think I can just remove that on this side. I think I can just say that, you know. Is it, this is this, right? Just so I'm clear. Okay. Now we're talking. Because if that's that, and this is working, and I also rewrite this. No. But all this works. Everything, this is all true. can I do this division? I think the problem is this division right now. No, that can't be right. Can I write this as I feel like this is a valid rule, right? Like if you have this, it should all cancel. Just because I feel something that I did them all cancel. M is equal to M mod K. Here I'm saying M is K is J. J M over J. It's so close.
right? Like this is very, very close to this statement. So what's wrong? What's missing? We're gonna say there's no n's in here. So every time we see a m, we're gonna replace it with n mod z. Sorry, n divided by z. There's only two letters in this equation, right? So we have n over z. And the only difference is the parentheses. J plus j parentheses right here. If I could move these parentheses, right? If I could do this, you don't see how that's the same little program. I see how it's the same, but maybe my eyes are playing tricks on me. Isn't that the goal I started with? I have to fill in the variables here. And J, right? What's wrong with this? What is different? What is different that what am I not seeing that is different? N divided by Z is right there. Divided by mod J right there. Plus J times N over Z divided by J. It's the parens again. What are the conditions for div assoc? Div Is that true? Yeah, what I meant to do is this. If I say like, so like div mul would be like nat div mul. Like, this is what I have, right? This is the same thing I have. Okay. And these are all, damn it. It's not a good idea to do anything like to, to mess with something that's like outside of this range. I don't want to touch any line outside of this range. Any lines in between here, I can do whatever I want. This is the same. And if I can reach this line, I'm good. But this is not, like if you divide by 4, that's the same as dividing by 2 and dividing by 2. Right? So that this should be this. This should be the same. Right? No. I think because it's not on nat, right? That I don't think I don't have a division monoid. This is the same. A divided by B times C. A divided by B times C. A divided by B. A, B, C. Exactly the same. There's no nat version of this? Nat, div. I got nothing. It's obviously true. It says a possible counterexample. I think this is pretty almost exactly the line I wound up last time. From a completely different path. I moved that to another folder, but okay. I thought I had a bunch of lean files in there. So I moved them somewhere else. All right, it's time to ask for help.
I don't know what I can do here. N Z ZJ. That's all it are. These are nats. I don't even need the middle part. I just need to I just need to I want to make very certain. I cannot remove those parentheses. Here I can remove the parentheses. Look at that, you can't remove those parentheses. That's okay. Okay, so this is the first statement. It needs to be right here. This is the second statement. It needs to be right here. I'm just looking to see if there's like any other place. Like this is so frustrating. I'm gonna check this in with this one line. Uh, just one pair of parens away. Wasn't it called like div a soap? Nat div all div a soak. Like, is there a step that I could have taken? Like, I know this is true. It's absolutely true. Yeah, I don't know. I don't know what else to do. I'm gonna ask for help, and I don't know. Maybe this is the end of the story. I back myself into a corner, and I can't prove the simple fact. Rewrite the whole project using rational numbers. I don't know. Hopefully, someone can help. I'm done. Thanks for watching me suffer. See you again soon. 7.5, almost 8 hours. Ridiculous.